Hello, it's about time I made an update on this pick and place machine. I think the last time I made a video about this was February of last year, so we're heading for almost a year now, and you might think from the lack of updates on this that there's nothing really happening. But actually, right after that last video, I spent pretty much 4 months every day working on this, and for most of the rest of last year I was working on it pretty steadily too. But you might not think that from just looking at what we can see here, at least physically. There's not much that's changed. I can probably sum things up in a few seconds. We have RGB LED light ring with the webcam there, and we have another webcam and light ring pair on the back of the head there. It's facing downwards, of course. There's a couple of load cells, an off-the-shelf one and a homemade one there. A little clicky switch here, and a curiously shaped piece of machined aluminium on the side of this vertical belt, which also looks like it might be some kind of load cell maybe in the future. And that's about it for the physical changes. So what the hell was I working on for almost a year? Well, I decided to make my very own motion controller and all the user interface and stuff to go with it completely from scratch, so that's not using OpenPNP and not even using anything from LinuxCNC either. So that's what this video is going to be about, and as such, even though it's kind of a part 3 in my pick and place machine series, I'm not going to call the video part 3 for that, because it's not really about the machine as such. It's more about the software that's going to be running it.
Anyone who's looked into this kind of software will pretty quickly come across this OpenPNP project, which is a very capable, full-featured, well-documented, well-used, well-supported, at least there's very active forums or mailing lists, and it's under active development too, and it's free and open source, so all the good stuff. And so of course that was my first plan. And the way this works typically is you have a computer, and your computer will be connected to some sort of a motion controller, and typically that's some kind of a 3D printer board. Seems to be pretty common. I've got some listed down here as recommendations. But things like CNC controllers like TinyG, Gerbil, Marlin and other 3D printers, firmwares are pretty commonly used as well. And they'll be connected to the computer typically by a serial connection, or alternatively you can also use a TCP IP connection as well. And I wanted to use LinuxCNC for this because I've been working on my little weenyPRU controller, and I wanted to use one of those with the Raspberry Pi to do this connection. Now unfortunately LinuxCNC is not very well set up to receive G-code commands over the network. It's mainly only set up to use files, so it will read in G-code from a file and run it. So I had to make this in between sort of a server thing to pass information coming in through a network connection to the LinuxCNC subsystem. And I also added some of these commands that are rather specific or highly recommended for use with OpenPNP, like this one, M400, which will wait for everything that's happening to finish and then it will reply. And so I set this up and I did a whole bunch of testing and development and wrote all these docs here and described how to set it up with OpenPNP, how you can get it all running like this. Here's a little clip that I took at the time when I was doing some testing of that. On the top left we have LinuxCNC, below that there's a webcam, in the middle is the server that I was just talking about, that's the output from that, and then on the right hand side we have the OpenPNP screen. And this is just the test job in OpenPNP, so there's no actual pick and placing going on, but this is just to test the connection and check that everything's working. One of the things that attracted me to using LinuxCNC for this was this path blending feature, which is controlled by the G64 G-code, and that lets you, instead of going all the way up to a corner and stopping before moving away from the corner, you can tell it to sort of take a little shortcut and curve around that corner or blend those two path segments into one sort of movement. And it's a little bit smoother movement, and I think it might be a little bit faster as well. Here's a little comparison of the blending versus no blending. At slow speeds it doesn't make any difference because the blending only kicks in when you are going fast and you want to cut around a corner quickly. So this is what it's like with no blending. And this is what it's like with a little bit of blending. Unfortunately, it turned out that when being fed G-code commands by my G-code server, LinuxCNC would start moving too quickly and it wasn't able to do these blendings sometimes. So all of the corners that we're seeing here are supposed to be curved around in this like shortcut kind of fashion. But when the commands weren't coming in quick enough, it didn't have enough of a look ahead to know where the curves should be placed. Another thing I was hoping to achieve was for instead of OpenPNP to send every little movement, for example in this pick and place stuff, quite often a movement is to move up and then across and then down. So that would be 3 G-code commands being issued from OpenPNP to LinuxCNC. But I thought it'd be nice if you could just send the final destination point and have LinuxCNC, by way of O-codes or these little stored procedures you can write, have LinuxCNC just figure out what it needed to do automatically so that there'd be less communication necessary, and this would also allow the blending to work correctly. But after quite a bit of discussion in the OpenPNP mailing list, it seemed like it wasn't going to be very easy to do that, at least not without disrupting quite a lot of the way OpenPNP does things. Another thing that was in the back of my mind all this time too was the concept of jerk limiting, or constant jerk trajectories, or S-curves as they sometimes called. And this is helpful to reduce vibrations and lower the settling time when the machine stops and you want the camera to be nice and still. So I'll put a link to this if you want to have a look at that. And I came across this page here, which was very helpful for me to figure out, basically to give me the confidence that I could actually program this. LinuxCNC does not do this kind of S-curve movement. There is some kind of provision in OpenPNP or some kind of approximation or synthesis of it, I think. Not exactly sure how it works, but I didn't really trust that coming from OpenPNP and then going through my G-code server to LinuxCNC. I didn't really see that working out too well. Also around this time, I'd been working on my weenyPRU, and I was starting to feel like I finally understood more of the inner workings of LinuxCNC, or at least as it pertains to communicating with an external real-time unit. So that brings us up to about a year ago, where I first started to seriously think that maybe I could make my own controller for this. And I was also thinking around then about the differences between what a pick-and-place machine requires and what we have in the typical CNC controller or 3D printer controller where we're sending G-code. And there's a lot of things that are kind of the opposite actually, so I've listed them up here. For CNC router or 3D printer, we're mostly just sending information one way. As I mentioned before, for LinuxCNC, we just read it out of a file and then we run it, and that's it. There's not really any information coming back from the machine into the computer. Whereas for pick and place, it's the opposite. We need lots of times we need to stop and wait for the machine to do something. For example, if we want to look at something with the camera, we have to move the machine to there, wait for it to get there, and then we can use the camera, and so on. And so it's the information just going back and forwards all the time, and each side of the system has to wait for the other one, and it's sort of ping-ponging backwards and forwards like that. For 3D printing and routing, we have pretty complex geometries. For example, G-code, you can have arcs and curves and I think maybe even helixes and things like that. And the exact movement is very important because you're trying to cut a shape out of aluminium or whatever, or you're trying to 3D print something. But for pick and place, we're pretty much just going in straight lines all the time. And even if we sort of wiggled a little bit on the way there, it doesn't matter. It's only when we get to the end point is what's important. For 3D printing, the control of the velocity is important as you're moving, because if you're cutting through plywood, you want to be moving at a different speed to when you're cutting through aluminium, for example. And for 3D printing, you need to extrude at the right rate. But for pick and place, even if we go slightly faster or slightly slower on the way to get somewhere, it doesn't matter, because we're only moving through air. It's just when we get to the end point that it's important. For 3D printing, typically we don't change acceleration or jerk settings during the run, at least not that I know of. But for pick and place, that can be very helpful because sometimes you're picking up something that's very light. For example, a 0603 resistor, you can pick that up and then move as fast as you like. It's not going to fall off the nozzle. But sometimes when you're picking up something that's a little bit heavier, like a larger IC component, for example, you might want to slow down your acceleration and jerk so that doesn't fall off the nozzle. So anyway, none of this is to say that using a 3D printer firmware is not going to work for pick and place, because obviously it does. There are thousands, well, probably hundreds at least, people using OpenPNP perfectly fine, but it just seems a little bit shoehorned in. It took things that were available and made use of them. And I was starting to think that wouldn't it be nice if there was a system that was purpose-built from the beginning to do this kind of a job? Another thing that I was thinking about during this time was the whole concept of flyover cameras or flyby cameras. This is one of my videos from about a year earlier where I was experimenting with an external microcontroller based camera as a flyover camera here, and some of you might have seen this video already, but it's just taking some photos every 20 something milliseconds, and the idea with this is that the bottom camera would be able to look at parts on separate nozzles very quickly just using a single camera. So for those of you who are not really familiar with that, if you have a machine with multiple nozzles like this and only one camera, the typical way you might do that is like this. So each nozzle would be held over the camera so that it can see what is on the nozzle, and that works perfectly fine, and seems like pretty much every hobbyist machine out there does that. There are other ways to do that though if you have some more sophisticated hardware. For example, this machine, you'll see it picks the parts up one by one, but then it zips across this camera very quickly, looking at all of the nozzles in one go like that. So it's almost too quick to even catch what's happening. Well, this machine, believe it or not, is kind of slow compared to some of them out there. There are some amazingly fast machines. But anyway, so this is what I'm talking about when I say a flyover camera, and even though I just said that there's no hobbyist machines out there, I think this might be a hobbyist machine. He's got this very interesting situation where the camera, this white splotch here, is built into the sled of the machine. So every time the machine goes over the top to reach the PCB, it's going over the top of the camera, and so it can look at the part on the way past. Quite nifty. So I'm not trying to say that I have solved this problem. I'm not even saying that I've tackled it. I'm just saying that this is another one of those things that seems to be a bit tricky to work into the traditional 3D printer firmware or CNC router kind of controller. And I was thinking again, it would be nice if there was a system that was designed from the ground up to take into consideration these things a bit more. So as I was gradually becoming more interested and more confident in making my own software for this, the final thing that tipped the scales was discovering this blog post here by Shuhao Wu. It's called Real-Time Programming with Linux, and it's very good, very helpful. It was like the perfect thing that I needed. So he's describing, what we're dealing with, what problems you're going to have. It's 4 parts in this blog post series, I guess. And he basically goes through and explains everything. And there's some source code examples, including how to deal with transferring information from the real-time to the non-real-time sections of the code. That's quite important. I didn't do it how he's doing it. I'm not going to go into details there. This video will get way too long, but basically, you have to deal with all this stuff. So I'll put a link to this in the description. You can have a look at that if you're interested. I found this extremely interesting, and he's got some code on GitHub as well somewhere telling you all about it. And I was just so excited to find this. Yet another thing that I had been thinking about all this time, it's amazing how you can fit all this stuff in your head, isn't it? Was how convenient it is that certain kinds of splines automatically have this like acceleration and deceleration and jerk limiting, not really jerk limiting, but they don't have infinite jerk as you get with a constant acceleration trajectory. A little bit too much for this video, I think, but anyway, certain kinds of splines are very convenient for this kind of movement. So what I thought I might do as my first test was try and make a spline type movement, and I went with one of these B-splines because if we look at this, if you move these control points around, let's say I make this first segment vertical, and we could pretend that this is picking something up on my pick and place machine, it's going to start up going vertical. At least it's tangential at this first point, which is quite convenient. And then let's say we want to come down and we want to pick something up and put it over here like that. As you move these control points around, we make that one vertical as well. We get a very nice vertical to vertical, but a nice smooth transition and acceleration in the velocity. Everything is like continuous. I'll put a link in the description to a very good video about splines, by the way, that I watched that sort of finally cemented my idea to try this as my first example. So for my first test, all I wanted to do was just send the positions of this varying over time to my weenyPRU board and have it move according to this. And this is how it turned out. Here's some other arrangements of B-splines. So I was feeling quite pleased with myself for writing my own real-time motion controller, albeit just a little hard-coded test. You can hear me typing in the command and then hitting enter each time there. But yeah, the smoothness of that movement was very encouraging, and so I looked into those splines a little bit more, but ultimately I abandoned that. And the problem with these is it's a little bit awkward to get things in absolute values. So you can see the height that it gets to here is not really based on anything that you can really look at. I think it's actually 1/4, so this height here is 1/4 the distance between here and here, roughly. So you can kind of look at it and infer where it's going to go, but you don't get to say exactly where it's going to go. And that turns out to be actually not so useful. So I ended up not using splines for anything after that, and I just went back to these, went back to this, and I sat down and spent a few weeks just to make sure I fully understood this, and I made a little test program to check my results and everything as well. And here's the GitHub repo for that. We're on to our third GitHub repo in this video, aren't we? This is called SCV S-curve, right? And I made this so that it could be a standalone trajectory generator, and there's instructions on how to use it there, so you can use this kind of code to set up your own control points and then get a curve that moves between them. So let's have a look at this visualizer utility that I made to go along with the SCV code, just so that you can get a look at things in 3D and play around with the numbers and see what they'll do. And we have a little graph over here that will show you also the values of position, velocity, acceleration and jerk at any point along the trajectory, and we can hit the T key to play visualization with this white dot showing how something would look moving along that trajectory. The dots are color coded here. Each of the colored sections is a constant jerk segment, and there'll either be 7 or 5 segments along each one of these lines here. The dots are every 100th of a second, I think, but very importantly, we need to be able to calculate the position of this at any point in time, no matter how fine. So if I turn the speed scale down to something extremely slow and run this again, you'll see, well, it's barely moving, but you can see it's sort of moving along there. So this is very important, because when we're running this with the pick and place machine, we need to get a position at every 1,000th of a second where it's going to be, where we want it to be anyway. And you can fast forward it if you want to by making the speed higher than 1. Let's put it back to 1 for the rest of this. And so obviously we're not doing any blending right now, but if I turn the blending on in the planner settings, so it's set to none. And the first thing I tried to do was this constant jerk segments, and the reason I wanted to do that is so that the resulting trajectory or the movement would obey all of the jerk and acceleration limits that I've set out for everything. So that's what these lines are here. You can set them separately for each axis if some of your axes are able to move faster or accelerate better than other ones. And so the corners here are made up of 2 constant jerk segments. So the red bit here is decelerating, and then when we get to the middle of the corner, we accelerate out of the corner, just as every good racing driver knows to do. And we can also change the jerk to the minimum or the maximum. I had that somewhere. Let's see, where is that? Control points. All right, so at the moment we're looking at all max jerk corners, which means that we wait until the last possible moment where we can still perform this turn while obeying the jerk constraints that we have set. Minimum jerk means we start turning as early as possible, and the corner will be much smoother but also slower, and we take as much room as we possibly can to get around that corner. What's kind of interesting about this is the max jerk or min jerk has no effect on the total time. So if you look down here, this graph shows the max jerk at the moment. It's about, what is it, a little over 6 seconds there, which is faster than if we don't do any blending. But if we set this to all min jerk, we'll see that the value of these jerk numbers here goes way down, but they take longer, right? So each section takes longer. And overall, the time doesn't change one tiny bit if I switch between these. Isn't that interesting? I didn't expect that, but it does kind of make sense. So like I say, that was my first plan. But what I discovered when I actually started running this on the machine is that when you're using the speeds and accelerations and distances that I want to use for an actual pick and place job, the restrictions that we have on this jerk and acceleration for the corner meant that it couldn't really be used very often. So for example, if we move some of these control points around, they're in here, and let's move point 0 up a bit. So point 0 is the starting point there. As I get closer to that corner, there comes a point where there's just not enough room to fit in the necessary turning and also obey the jerk setting that we want to follow. And sadly, this was happening on just about every corner that I was trying to run it on in an actual pick and place type of movement. So I ended up abandoning that, and I'm not going to be using that. What I have instead is something that was much less of a headache to program, and that is just this thing called interpolated moves. And what that does, I'll just put it back to none for a second. What that does is it takes this segment here, and instead of going all the way to the end here and stopping, it starts moving along the second segment there when it's at a certain point along here in time. So for example, halfway would be here. We could start moving horizontally or towards the back of the box here, and we could start doing that early, and that looks like this. Oh, whoops. I need to change the scale here a bit. There we go. There we go. It looks like that. And depending on the acceleration and jerk settings you have, sometimes it doesn't look very good, because if I increase it all the way up, you basically end up with just a straight line like that. So you don't want to do that, really, I don't think. But what I've discovered is that a setting of somewhere between 0.5 and 0.75 looks pretty nice. It still doesn't look very nice on this example that we're looking at with these particular jerk and acceleration numbers. But when you look at this in actual pick and place movement type of numbers, most of the corners look a bit more sensible like that. But more to the point is that when you're using this style of blending, you can blend on every corner no matter what, because we're actually not following the jerk limits anymore, which is a little bit sad. Well, to be honest, if you're turning 90 degrees, you're still following the jerk limits, because you're moving orthogonally, perpendicularly to this line, in which case the jerk in one direction doesn't affect the jerk in the other direction. But if you're turning a corner like this one down the bottom here, oh, and you can see this red dot. This red dot signifies that one of the limits has been violated. And the reason it's been violated is because this corner is an angle of greater than 90 degrees. If I just turn the blending off again. So this corner looks like about 135 degrees. So what's happening is, before it's reached here, it's already starting to move upward. And because the next movement is it's in the same direction as the previous segment, it's not going to follow it's going to be going too fast at this point. The acceleration and jerk will still be followed, but the velocity will not. I think that's what will happen. However, in the typical pick and place job, we're mostly making only orthogonal corners like this one here. So I've decided that it doesn't matter, and given the simplicity of programming of this and the fact that we can also nice and smoothly adjust the corners like this, I've decided that this is a much better overall plan of attack for making a pick and place movement. And it's also nice that this does actually affect the overall time of the job or the trajectory, so it's nice and smoothly adjusting one way or the other. So you can come up with a nice compromise between how you want your corners to look and the overall time of the trajectory. Let me just talk about these blend override settings a little bit more, because there are some points later in the video where I'm changing the setting and nothing happens. It kind of looks like maybe I made a mistake in my programming. Oh, how dare you even think that? But there are some restrictions that are not so obvious that we'll have a look at here. So let's say we have a couple of segments. We're moving up for 1 second and then sideways for 1 second. Now the blend overlap is defined in terms of time, not distance. So let's say we have a blend overlap of 0.5. That means that we're going to try and start halfway through this segment in time and then finish or continue onto the segment halfway through that one. And the overall result for this, it's quite a nice case where it's all symmetrical. The blend duration will therefore be 0.5 seconds, and this movement overall will take, instead of 2 seconds, it's going to take 1.5 seconds. And if we had a blend overlap of 0.75, it means we're going to start a quarter of the way through this, and we're going to spend 3/4 of this time blending into the next one, so that we get to here 3/4 of the way through that one. And again, because this is symmetrical, it works out quite nicely, and the blend duration will be 0.75. But when we have a case that's not symmetrical like this, so let's say our first move takes longer than the second move, which is faster, it's only 0.5 seconds, This time when we set a blend overlap of 0.5, it's going to be limited by the shortest time available. So the blend duration can only be a total of 0.25 seconds, meaning that instead of starting halfway here like you might expect, we can only start 3/4 of the way through this segment. There's also some more restrictions that come along when we have more than one segment in a row. So let's suppose we have again a bunch of segments that are all 1 second long, and let's see what happens if we start off over here trying to put in a blend overlap of 0.75. We can start here on this first segment, we can just put it here, that's fine. But when we get to here, we end up with this 3/4 of the way along that one. And each of these corners is being calculated separately. So we've managed to do this one okay, but when we come to blend this second corner, we're stuck in a situation that's never going to work because we can't start 3/4 of the way back here anymore. So for these segments, or for these corners in the middle, or the interior corners, or interior segments I'm going to call these, we're forced to reduce the overlap to a maximum of 0.5 so that each of these overlaps can play nicely with its neighbors. And that kind of spills over into these ones as well, so the beginning and the ends also then have to be pretty much the same. And so the overall path for this will look kind of like that. Now that was okay, but it kind of left a little bit on the table regarding these end segments, the beginning and the end, because as I said at the beginning, we can actually put this point at the quarter mark and it's not going to disturb anything on the other side because there is nothing on the other side. This is the first segment and that's the last one. So for the first and last segments, we have a special case where, provided these segments are short enough in time, we can actually move this to the original place that we wanted to. So that would look a little bit like that. So it's starting at the original 0.75 or 0.25 I guess here, and then it's finishing at the 0.75 mark at the end there. And as it turns out, when you're doing pick and place movements, you very often have a short fast movement at the beginning, a longer movement that takes more time to move sideways, and then you have another short fast movement, place the component down. So this works out very well in the context of the pick and place movements that I'm doing, and it means we can chop off a decent amount of time at the beginning and the ends and make the overall movement nice and smooth as well. So this is what that would look like overall. We still want to have a little bit of movement at the ends that's straight. You know, we don't want to be blending as we come down to put something into the solder paste, probably. And here's a little demo of the obligatory liquid settling test at 2 different jerk limits. So let me give you an overview of the parts of the system and how they connect together, and then we'll look at the software itself after that. The core of everything is a Raspberry Pi 3 or 4, not a Raspberry Pi 5, at least not just yet. Hopefully that should be doable in future. And this needs to be running some kind of real-time version of Linux. I'm using Preempt RT, which works great. There is another one out there, I forget what it's called. I have not tried that one. I think it might be okay, I don't know. And running on this Raspberry Pi, we have a little program called PNP Server. This is just a command line program. It doesn't have any graphical user interface. And inside this program, we have 2 main sections, real-time and non-real-time. The job of the real-time section is to run a very precise and predictable and consistent loop. Every 1,000th of a second it updates on the dot, like, you know, no delays or jitter or latency or anything, we hope. And the main job that it has is to figure out where should the machine be at any given time. So if we're moving along a trajectory like this, little white dot, it has to figure out where the little white dot is. It does not actually calculate this trajectory. That's done by the non-real-time section, which is where all our user interaction is going to be happening. So this non-real-time section is a little bit slower. But nevertheless, these 2 sections do need to be very tightly linked. And the real-time section is relaying information to the non-real-time section at also 1,000 times per second. The non-real-time section is not quite so verbose because mainly it only needs to talk to the real-time section when the user is giving some sort of a command to it. Anyway, so outside there we have the weenyPRU, and this is connected to the Raspberry Pi over the SPI interface. And this is being read to and written from also at 1,000 Hertz. And the weenyPRU is then connected to whatever stuff you have outside that. So you've got stepper motors, you've got your digital inputs and outputs, I2C sensors and all that stuff. So there's still pretty fast updates going on in there. Right, then we have a whole other computer, or it could be the same computer. So mostly what I've been using or testing with is Fedora Linux. That's my main computer. Also, every now and then I compile and test on Ubuntu. That seems great. macOS it builds and runs, but I haven't really done much testing on that, and I'm not sure how the webcams are going to work. So macOS is just sort of low priority at the moment, but Fedora and Ubuntu should run great. And then on this, we have the PNP client, and as you might expect, that connects to the server, and the server is pushing updates. It's sort of streaming constantly the output from this real-time section. So I decided that 200 Hertz updates for that would be fine. And then inside the PNP client, we have, of course, something for the user to look at. So that's the user interface. And I'm using Dear IMGUI, which is, it's made for games, but it's very useful for other things as well. And ideally, you would want this computer to be able to update at 60 Hertz, just to give a good user experience. But I think anything, say 30 and above would be fine as well. So one of the slight downsides of what I've made here is that this computer on the right hand side needs to be fairly powerful in the graphics department to be able to do that. At the moment I'm running things over Wi-Fi and it works great like 99% of the time. Every now and then there's a little bit of a jitter, like you're trying to jog the machine and it sort of doesn't quite move when you push the keys on your keyboard. There's a little bit of a delay. That could be improved greatly by using a wired connection instead of Wi-Fi. But even better would be if this was all running on the same computer, then you wouldn't even have a network connection at all because it would be localhost. But the only way to really do that is with a Raspberry Pi 5, potentially. So I need to get hold of a Raspberry Pi 5 and figure out if it can run the graphical interface side of this as well, because that would be cool. Anyway, so over here, this client is, of course, connecting to the webcams and looking at the image data coming in from those, and it can also connect to serial ports to read and write information from those as well. As far as the supported hardware goes, we already know we need a Pi 3 or Pi 4 and a weenyPRU. The vacuum sensor will need to be one of these XGZP things. These are I2C vacuum sensors, and I think this XGZP refers to the family as a whole. I found these on AliExpress, and there are actually some other numbers in the model name usually, but these numbers, I think they refer to the range of pressures that each individual model is made to sense. I'm using this one that goes from -100 to 0 kilopascals. Seems to be pretty much perfect for this application, and it comes on this handy little breakout board, and this little nozzle bit at the top fits perfectly into my silicone tubes that I'm using. The webcams will need to be something that is supported by libUVC, which is quite a lot of webcams out there, I think, and it will need to be able to do 640 by 480 resolution, which is also pretty much all webcams as far as I know. I'm only using 640 by 480 at the moment. It seems to be sufficient for what I need, and I think I've actually hard-coded this in a few places, so if you use another resolution, it's probably going to crash. So we'll have to figure out something a little bit nicer to deal with that later on. And 30 frames per second, most webcams can probably do that at 640 by 480, and that's a pretty comfortable rate. You wouldn't want it to go too much slower, I don't think, and I don't think you really need to go faster than that. You will also want to make sure that the image stream that's coming from it is not compressed, so something like YUYV or YUY2 is what I'd recommend. You can also use Motion JPEG, but it's not as good for this purpose because the image compression that it does makes each consecutive image slightly different from the previous one, and it looks a little bit shimmery and jittery almost, and the colors are not very well represented either. For the load cell amp, if you want to use a load cell for probing, you will need to use one of the good old HX711s or one of the newer HX717s. The main difference in these, or the main advantage of the 717, is that this can do 320 Hertz output. The HX711 can do either 10 Hertz or 80 Hertz, depending on, well, let's have a look here. So that's one of these. All my Arduino bros out there will probably recognize these. These are very cheap. That's $7.30 for 10 pieces there. Unfortunately, the way this breakout board is arranged, it is only 10 Hertz output by default. But if you take this pin here, the second from the top on this corner, and you detach it from the pin on the board and you bend it over to the side a little bit so that it's connected to the one on the corner, then you'll get 80 Hertz, which is pretty much a necessity for this. The 10 Hertz rate is just not going to work. You need something faster. 80 Hertz is pretty good. You don't really need the HX717. I just thought I'd try one of those to see how they worked. If we look here on AliExpress for them though, you can see I've searched for HX717 and I've got No convenient breakout boards. All I can find is the bare integrated circuit itself. So I took it upon myself to make one of these, and from JLC PCP I got a few of these, designed these. It's not much to it really, so I'll put a link to something in the description where you can clone this project and make one yourself. And for steppers, or stepper drivers that is, if you want to use UART control to set the phase current of your motors, you'll have to use the TMC2209 drivers, because those are the only ones that I've tested with this. I think the TMC2208 might work as well, but I don't know. Okay, so we saw before that we have a server and a client, and this slide just explains what the tasks are for each of those. The server, for the most part, is updating everything at 1 kilohertz. So that's the movement of the machine, the reading digital ins, writing the digital outs, writing the PWM out. There's just one of those. I'm not using it, but it's there if you need to use it. Reading the vacuum sensor and the load cell. These are actually not updating at 1 kilohertz. The vacuum sensor seems to be running at 150 hertz, and then the load cell, well, that will depend on whether you're using the HX711 or the 717. Overrides is something I'll get to later in this video. That's updating at 1 kilohertz. And then if you want to use UART control for the current of your stepper motors with the TMC2209, that's also updating on the server, not at 1 kilohertz. So this is actually only updating at 1 hertz. And then we have two separate states, separate to movement. So movement is where the client is actively controlling the machine and telling it what to do. But then we have two other states where I think most people watching this video will be familiar with what this is, but basically the client can hand over control to the server, and then the server can control the individual movements that it does for a while because it knows what is required to do this. And then over on the client, let me also make a point here. The weenyPRU can only control 4 stepper motors, so the X, Y, and Z coordinates are coming from the trajectory generator that we saw before, and then there's a fourth one which we're going to use to turn the nozzle, rotate the nozzle. So what this means is that this machine, or this firmware, is only going to be suitable for a single nozzle machine, and that's fine for me. That's all I have. I actually did a little simulation to see how much my job would speed up if I had 2 nozzles, and it was only about 10%, so not super worried about having just a single nozzle, and I'm already biting off quite a lot to chew on by making this thing in the first place. So we're just going to be dealing with a single nozzle for quite a while, quite a long time. So don't ask me about dual nozzle setups, all right? Okay, over on the client, obviously we're displaying all the status to the user, and then we're sending commands to the server to tell it what to do. We're reading the cameras and displaying the cameras on the screen, of course. And we're reading and writing the serial ports. There's an SQLite database which we use to store the job information and part information and just whatever you want really. And we also do some logging. And then we have AngelScript running to run scripts, which is a jolly good thing because there is no high-level job processor in this firmware. Everything, all of these parts and bits and pieces that we're looking at here, they're all going to be tied together by script that you have to write. Well, probably I'll write quite a bit of it that you can modify. It's probably how it's going to go. But if we look over at OpenPNP, there's a page here that describes the job processor, and it says there's two steps. There's like a job processor, and then there's a job planner. We have things like fiducial checks, board location checks, pre-flight steps, and we've got some planning. We figure out whether we need to change nozzle tips or calibrate them. Then we figure out where we're going to go and pick things up, and then we align them using computer vision, and we do all this stuff. So this is what I would call a high-level planner, and that is just non-existent in my software. So that script there is going to become very important. Anyway, let's finally take a look at how this thing looks and runs.
Before we look at the software, I'll just recap what the hardware is for those who haven't seen it in my earlier video. So the server is running on this Raspberry Pi 3, and it's connected to the weenyPRU there via this thing that I'm calling a Raspberry Pi hat tip. It's just a little board like that, and all it does is carry the signals through from one side to the other, but it flips them over. And the purpose of that is so that the Raspberry Pi and the weenyPRU can both be facing upwards. If you didn't have that, you could turn the Raspberry Pi over and plug it in that way, but then it's dangling over the edge and it's not very secure, and I just didn't like it like that. So on the Raspberry Pi we have a whole bunch of wires. There's a stepper driver there that's for the rotation nozzle, and that's running on 12 volts. The other steppers are running on these external stepper drivers on 36 volts from my 36 volt power supply over there. And we have a NEMA 23 with an optical encoder, a NEMA 17 with a magnetic encoder, and then there's a NEMA 14 for the vertical, also with a magnetic encoder over there, and then a NEMA 8, which is the 12 volt one that's running the nozzle. And then over here we have just a bunch of MOSFET operated switches that also run on 12 volts, and they're just taking a digital out from the weenyPRU to switch these kind of little nozzles, sorry, not nozzles, valves for the vacuum. So I've got one there, and then I've got a couple more of those valves riding on the head there, because they're quite small and light. They'll fit in anywhere just about. And then we have, for sensing the vacuum, there is this I2C vacuum sensor that we just looked at before. And we also have load cell. I've got two load cells over here. Well, that's the load cell there. That's my homemade one. Actually works quite well. Only one of these is connected. We can only have one at a time, so we're just using the store-bought one for this video. And over here we have an iomixer, which is also connected to the weenyPRU by a couple of digital outputs, and it is connected through these lines to the RGB LEDs there and there. Unfortunately, they need to be in sequence if you want one iomixer to run them. So this cable goes down, and then it comes back, and then it goes over to there again, so that they can be in series. And also connected to the iomixer, we have over here just one of those regular USB to serial adapters. I think that covers everything. Oh, and the client is running on my main desktop computer down there.
So as I mentioned earlier, the server runs on Raspberry Pi. That's what we're looking at here, and it's just a command line program that we run like this, and it loads a bunch of configuration parameters from a JSON file, and then it spends a few seconds figuring out what the load cell value looks like when it's not doing anything. So we don't need to look at this anymore, so I'll put that in the background, and we'll look at the client. The client has this nifty 3D model. At first I added this just as a gimmick. I wanted to see if I could export my CAD files from Onshape as 3D models, and that would give me a nice, very precise model of my machine, because these are the same files that I used to cut these pieces of aluminium with. It turned out to be actually kind of useful to run as a preview to see how the machine would move before you do the actual move as well. So it's a little bit more than a gimmick at the moment. Anyway, over here we have a bunch of menus, and from each of these, or most of these, we have some sort of a panel that shows up like this. You can move these around, and the most fundamental one is this status panel. You can see we have a server connection, and this is the last time we received a packet from the server. It should be mostly 0 to 1 milliseconds. And it also shows that the SPI connection between the Raspberry Pi and the weenyPRU is working as well. That's why it's green. And then we have some other values coming in at about 200 Hertz, although of course, as you see at the bottom, the frame rate that we're looking at, this is only 60 Hertz, so we're not seeing all of the 200 Hertz. There is a plot here which does show the 200 Hertz values, so you can graph those. You can see at the bottom there we have, these are the load cell values. If I touch that load cell there, see the values changing like that as I do a little bit of a tap 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 on the load cell, and we can have a look at the details of that there. So this will show also the position, velocity, and a few other values there you can see. So that's plots, and so I'm going to keep this window open. Like I said, this is showing us all of the information, and we've got some buttons down here which are mostly just for testing at the moment, so they're all kind of plonked in here roughly. This will probably change a fair bit in the future. Another view we have that's quite useful is the logs. I'll put that up here. We can sort of see when you get some warnings and errors and things. And then let's look at this server panel, which is probably the first thing you would be looking at when you're setting up the machine. So we have the host name, or the IP address in this case, of the server that we're connecting to, and then all of that information that we saw at the beginning that was pulled off of the Raspberry Pi, pulled out of the JSON file to set up the configuration, that was configured from here on the client. So steps per unit, unit being millimeters in my case. So this is how far or how many steps each of the motors has to move in order to do 1 millimeter. And then we have a working area which is defined also in millimeters. And in my case, for the TMC2209 drivers, I'm only using one of these on the Z-axis. Sorry, no, it's the rotation. It's the NEMA 8 motor that does the rotation of the nozzle. So I've set that to 16-step micro-stepping and 200 milliamps for the phase current. Then we have some limits. This is the what we were looking at with the trajectory generator before. So each axis has limits for velocity, acceleration, and jerk. And we can change those limits during the run of the program. And I'll show you how we do that later with commands. But at the beginning, there is a possibility for us to move the machine without setting any initial values. So there's just some initial values to use for velocity, acceleration, and jerk down here as well. And also initial value to use for the amount of blending that we want to do at the corners. But this is just when the machine starts up. We can override that with our program later on. Then we have the homing tab, which defines for each axis which pin should be triggered when the homing switch is tripped, and which direction the homing should go for that axis, how fast it should go, how far it should back off before the second approach, and so on. And then finally the position to consider that in the working space once it's finished the homing. And at the top here we have homing order, and for my machine I want it to home in the order of Z, X, and Y. So I want it to lift up first and then do the horizontal homing. Over here we have jogging. These are just the default jogging speeds. We can scale that here with this jog speed scale. So when it's all the way up to 1 on the scale here, this is the speeds that we'll get for each of these axes. And we have overrides, which I'll get to later. Load cell, this is where we set up a calibration for the load cell if we want to know values in, for example, grams, rather than just this crazy number that we get directly, the raw number from the load cell. Then we have some settings for probing, which I might explain a little bit later as well. But I'll just close this there. And so we can do a little bit of jogging here with the arrow keys, which I will do. So left and right, and then forwards and back. You can see it's a little bit choppy there because it's working over the Wi-Fi, so every now and then we get a few missed packets. Actually kind of okay at the moment. And then page up and page down will move up and down like that. And so the machine is actually moving at the moment, but if we use one of these other panels to figure out which webcams we have, there's only one at the moment. So if I open this, you can see we've got a whole bunch of settings that we can change. So we can fiddle with them manually here. Do I want to do that? Alright, just for example, I'll show you the saturation here. We can make it very colorful or not very, or just grayscale. We've got brightness and stuff, so on. So we can fiddle with these here, but you don't really do that so much. You mainly want to do that with script. So from script we can control all of these settings for each camera as well. So I'll just hide this down here somewhere, I guess. Needs to be open, I just discovered before. I can't close this, otherwise the webcam will stop updating. Anyway, so you can see we've got this webcam window here, and the head of the machine is actually at the back, so it doesn't match my picture, and that's because I haven't homed it yet. So let me just check. I can click home all to do, well, let me just click that. So you'll see that as it goes over to the side, it drives through until it figures out where it's supposed to be. And once all three axes are homed, then the picture that we see on here should match the reality that we see in the webcam up there. So now we can move this around, and it will respect the work area that we set in the service settings. So if we command the machine to move outside this range, it will refuse to do it. So it's going to be a little bit more sensible with movements now. Okay, let's try some programmed movements, and the most fundamental basic way to do this is using commands. These are a little bit like G-code, but not quite. You'll see as we go. And so we have this command list editor panel, window, whatever, and it's kind of like a text editor with tabs up here, so you can add more files if you want to. The most basic movement is the M command. So we have something like this. I'm going to move it to X140. So just to look at where we're starting from, we are currently at X40 Y140 and Z0. And the movement limits or restrictions are velocity, you can see these here, acceleration and jerk, like that. So if I move to X140 and I click preview, it will show me in the 3D view what that is going to look like. And probably the next most basic command is the wait, which is W, and we can wait for 1 second there, and then we can move back to X40 where we started. We preview that, go like this, and then down here we can see the traverse time. So from the preview, when it calculates what it's going to do, it'll show you that this will take 1.8 seconds overall. And we can slow down the preview if we like, if it's a little bit fast. We can slow this down here to like quarter speed or something like that. This is quite handy sometimes when you have got more complicated movements, you want to see what it's going to do. Unfortunately, the wait times are also scaled down, so you notice it waited more than 1 second at the end there. Alright, and then if we run this, we'll see that the actual machine moves this time, and if we want to scale the actual running down, we can do that over here with this slider, so about quarter speed there, and run like that, and we can speed it up while it's running. We can fiddle with the slider while it's running as well. If we want to change the movement limits, we can do that with the setMemoryNumber command, and then we need to say which limit we want to change. So at the moment the movement limit is velocity 1000 millimeters per second. We could say that we want that to be 200, and instead of taking 1.8 seconds, you'll see it's going to take 2.25 seconds overall, like this. And likewise we can set different jerk settings here and acceleration and stuff. So jerk is 50,000 at the moment, so let's change that to 1000, much smaller value, and you'll see it's a softer starting and stopping. And the jerk kind of limits how fast you can move overall. So if I put the velocity back to 1000, the jerk is still going to limit us so that we can't really get anywhere near 1000 millimeters per second. Not that we were before anyway. To get to the really high speeds, you need a longer movement. We're only moving 100 millimeters, so we're not really going to be able to achieve much speed. But anyway, this is what... It doesn't look much different actually. But anyway, you can see that we're able to set different jerk limits like this. Not sure how far I can go with this. Let's try 80. I think 100,000 is okay. Let's see. Yep, that looks fine. I just keep it on 50 most of the time. Let's put it back there. Now about the blending, let's make some more movements here. So I'll take this weight out, and you'll notice that it doesn't go all the way to the point that we told it to now if I run it. So just keep an eye on this little blue bit here. By the way, this is color coded so that it's blue where it's slower and red where it's faster. That's why it's blue at the tip here. But if you look at this when I press preview, it only goes this far now, and that's because it's actually blending, and it's a little bit tricky to see the blend properly. So I'll put another movement in Y in the middle. So we're going to go back a bit, and then we're going to go to 140. Let's see, I think that's right. Okay, so now you can see how it's blending around those corners. If, for example, we don't want it to blend somewhere, we can put the weight back in with a value of 0, so that it doesn't actually do any weighting, but it will get rid of the blend like that. Oops, did I run that with full blends? Let's see it with full blends. There we go. We can also control here the amount of blending that we want to do with set blend override. The default is 0.75, so this should not change anything, right? And we can make it smaller like this, but depending on what speed you're going, sometimes it might not have much of an effect. So let me also put some smaller segments in by doing a move. Oops, let's put that in. So here we'll go to Z minus 20, and then we'll come back up from Z minus 20 to 0. Preview that, see it goes down. Now because this segment is a bit smaller, it's going to show a little bit better how the blending override works. So if I put that back to 0.75, you should see not much of a change there. And the reason is that because when it's going down and back up again, it's actually blending this corner as well. And you don't get such a pronounced blend until you reach the end of the point where the end of like a stopping point. So if I put a stopping point in here, like a wait 0 there, with a space. Now if we preview that, we'll see that it actually goes all the way down to Z negative 20 like I told it to. And because it knows that it can stop at this point, the way the blending works, it knows that it can start blending earlier and do the full 0.75 of this segment here as a blend. So now if I make this to say 0.25 or 0.5, we can see that it blends less there, and we can even get rid of the blending entirely if we wanted to, so that it goes like that. But let's just put it back to the default of 0.75 while we do the rest of this. Now let's see how we can do some rotations. So I'll just get rid of most of this here, and we'll just have that 2 straight line movements that we had at the beginning, like that. It's going to blend though, isn't it? So let's slow it down. Let's see, 200. Okay, a little bit slower. There we go. Alright, so we've got 2 movements, and then if I want to rotate, we do that with the R command. So rotate, at the moment there's only one rotation axis supported, that's the A axis, and at the moment the actual rotation of this is 0, and you see, hopefully you can see I've put a little black mark on the front of this aluminium bit on the nozzle adapter, so that's where the 0 degrees point is facing towards us. So if we want to rotate that to 90 degrees during this movement, and then after we get there we'll rotate it back to 0 like this, and I'll preview this quite slowly so you can see the little arrow pointing forwards is at 0 degrees at the moment. If I preview this, you'll see oh, I need to put a sync in here. I'll get to the reason for that in a minute, but let me just put that there. Alright, so you can see it gets to the end and it rotates, it goes back, and then it's going to rotate again when it gets to the other end like that. And you'll also notice that there's some events showing up here. So at the time 1.46 seconds, the event rotate A to 0 is going to happen. Oh, well, the first one is at 0.62 seconds there. And if we run this, I'll slow it down. Whoops! I'll slow it down so that when we're running it, you can see that little black dot moving around a bit easier too, hopefully. But let's run it like that. Okay. Now, what is the point of this sync, and why do we need that? Well, let's see what happens if we move these rotations ahead of the movements that they're associated with. What that does is it lets them run concurrently, because the rotations will just run no matter what else is happening. It doesn't care what the movements are doing, so there's no actual synchronization unless you put this sync command in here. So now let's see, we'll preview this. Go. You'll notice that it rotates already, and when we get to here, again it rotates concurrently with the movement. And depending on how long that rotation takes, let's say this first rotation takes quite a long time. If we slow it down, it might not be finished by the time the second rotation wants to start, and in that case the program doesn't know what to do. It doesn't really make sense. So anytime we have a rotation followed by another rotation somewhere later, we need to have a sync in here to say that we wait at that point for the previous rotation to finish. And what that will also do is it will make sure that all previous rotations and movements are finished, so we're kind of at a state where everything is stopped and reset. And let's just run that so we can see that the machine actually does it. Now let's say we didn't actually want this event to be at the 0 point. Let's say we wanted the rotation to start a little bit after the movement has started. This might be important in cases where you've gone down to pick up a component out of the tape, and you don't want to start rotating as soon as you lift up. You want to let the nozzle lift up away from the tape a little bit and then start rotating. In that case, you can put a T parameter on your rotation and then give a number of seconds to wait. And we'll just go, so I can see it gets to here at 0.62, so let's make it 0.2 or something like that. And let's preview that. So you can see that event, this little green dot where the event is, has now moved so that it's not starting there, it's starting here, and the time is 0.19. It's supposed to be 0.2, maybe that's a floating point rounding issue. And if I just run this again at the slow speed, you'll see that the rotation doesn't start until it gets to that green dot. Like that. Okay, hope that makes sense. And let's say, like I said before, we could set the rotation limits like this. Set rotation limit to, currently the rotation limit is velocity is 3000. If we drop that right down to like 100, it's going to rotate much slower. So what's going to happen now is it's going to take so long for this rotation to complete that it's going to get all the way to the end of the movement and it's still going to be rotating. But because we've got this sync afterwards, it's not going to move again until the rotation is synchronized with the movement. So let's watch that. Rotate. Very, very slowly. Still rotating, so it can't get past that sync until it's got to there. And then it actually goes back. So let's run that. Hopefully it all works. That dot doesn't show up very well, does it? Sorry about that. And just to demonstrate how that's all operating, like the rotation is operating concurrently, let's say we want to go to X70. I'm just trying to put a little bit of a kink in this movement. So back up to here. Let's see what that does. Okay, so we've got a little bit of a bump there. But you'll notice that the rotation is just smoothly moving all the way through that bump. Well, on the way back it's just a straight line. But let's run that. And let's run it at full speed because that's always much more fun. And next I want to show you how we can control digital outputs. This is quite important because this is how you turn on and off your vacuum suction to pick things up and put them down. So let me get rid of these rotations, and we'll get rid of also that stuff as well, so we don't need to sync either. Alright, so we're just going back to the plain side-to-side movement like this. Alright, so to turn a digital output off and on, we use the D command, and to turn it on, we just put the number of the digital output. I'm going to use digital output 5 because the first 4 digital outputs are actually controlled by overrides, so attempting to change them here is not going to have any effect. So I'm going to use pin 5, which is this 5th red dot here, and I'm going to turn it on with 5. Then we're going to move to X140, and because this is going to happen rather quickly, I'll put in a wait of 1 second, and then we're going to turn it off by saying -5. So you just put the negative of the pin that you want to turn off, and then that movement should go back to there. So if we preview this, we'll see we've got 2 events. At the time 0, digital out 5 goes on, and at time 1.62, digital out 5 goes off, like that. And if you keep an eye on the top left here, when we actually run that, you should see these little red dots change from red to green and back, or one of them anyway. And we can put multiple pins on there. So let's say 5, 7 and 9 we want to turn on, and then 5, 7 and 9 to turn on and off, yeah, like this. So if we run that, we can see them turning off and on. And let's just get rid of these, and we can do the timing offset thing in the same way with these. This is very important. If we ever get to running flyover cameras and things, this could be quite useful. But for example, let's say T 0.2, after 0.2 seconds we turn that on after the movement has started. So again, that will shift the event from being here to being here at 0. I wonder why it says 0.19 instead of 0.2. But anyway, if I'll slow that right down a bit so so at quarter speed you should be able to see now this digital output will only go on after the movement has started. Ready, go. And it turns off after the 1 second wait at the end. Like that. Okay, now we need to look at some scripting, because like I said, scripts are how everything is glued together, and under this menu we can open a script editor. The script editor is very much the same as this command list editor, except In this one, we're going to be editing scripts, and the script language that we're using here is called AngelScript. For those of you not familiar with AngelScript, I'll put a link in the description to this website where you can read all about it. It's created by this very clever fella called Andreas, and it's been around for quite a while. I first discovered this in, I think, 2010, and ever since then it's been my first choice for scripting engine whenever I need to do something like this. And it says here it follows the widely known syntax of C, but obviously without the need to worry about pointers and memory leaks. And if we go to this page, we'll see some of the high-level features described a bit more. And I'll point out this one where it says, unlike most scripting languages that are dynamically typed, this one uses the same static types as C, which just means that, for example, the top 3 lines would be perfectly fine in JavaScript because JavaScript allows dynamic typing. So this B here, we don't even need to say what type of variable this is. We just say B equals floating point number, and then right after that we can say, oh, now B equals a string, and that's fine. But in AngelScript, that's a no. In AngelScript, you need to say right from the beginning what type each variable is, like this down here. And when we say that A is an integer, A has to stay an integer, at least in that same scope, from that point onwards. And if we go back over to the website here, we can, I'll let you look at this in your own time. It's all very well documented. You can see all the help topics in the side there. But for the most part, you can just pretend that you're programming in C and you'll get along pretty well. There are some exceptions occasionally that you'll come across, but there's not too many. Anyway, let's make a very simple script. So we have, void say hi, and then we'll put in here just a print, not printf. My hands type printf all by themselves, just out of years of habit, you know. So we're just going to print hello, and when I try and run this, it's not going to work because, as we'll see, it says could not find entry point void main. So if you don't specify what entry function you're looking for, it's going to try and find one called main, but we want it to use the entry function called say hi. Now when I run this, we should see it says hello down the bottom. We also have a preview button here, and the preview will do the same thing as the preview over here. It's not actually going to move the machine, but it will show you on the 3D view in the background what would happen if we did run it. Now there are a couple of other ways that we can trigger the script, and if we look up here, we have something called event hooks. So in this panel here, we see we have function keys and GUI buttons, which can also trigger a script. So if I look at the function keys here, and under my F6 key, I say that F6 should run the function say hi and not in preview mode. Well, it doesn't really matter because all it does is print something out. But now if I hit the F6 key on my keyboard, you'll see that I'm running that script that we just wrote by pushing the key. Over here we have GUI buttons, and for that I'll also open the output panel for this, so this custom buttons one. Over here we can see some buttons that are labeled in the same way as we have set up here. So if I add a new button, let's say video, well no, let's just do say hi, and then over here the entry function should be say hi, take the preview off, and a button has appeared over here. If we click this, the same thing happens, it just runs the script. So those are the 3 ways that you can trigger a script to start. There's also a third tab here called tweaks, and if we look in here we'll see a bunch of rows where we have a name and then a minimum and a maximum value. And again, if we open up another panel to see the output of this, which is tweaks, so I'll get rid of this custom buttons one. So now over here in my tweaks panel you can see we have some sliders like this, and they match up with the tweaks that we've set here. So I can add a tweak here, I can say how much. And then over here we have this, which goes by default between 0 and 10. We can change that to say 0 and 120 or whatever, like this. So my slider goes up to 120. And then in the script here we can access that. So I could say get tweak value how much, like that. Oops, like that. So now if we run this, it'll say hello 102.742 because that's what the value of this was at the time. And this is very useful if you don't exactly know what value or number you need to use. You can run the script, and while the script is running you can change that tweak. So we can do this. The wait times here are set in milliseconds, not seconds. in the command list they're set in seconds, so I might change them to both be in seconds. But anyway, let's wait for 500 milliseconds here, and so I'll run this, and you'll see it puts out a sequence of numbers, and as I change the slider here, the value that it's getting from that tweak will change. So this is extremely useful when you're just sort of twiddling and tweaking things to fine-tune a value that you're looking for. Alright, let's get rid of these then, and let's see how we can run a movement of the machine. So we can do run command like this, and then we can do, for example, mx140, and if we preview that, we'll see, you can probably see in the background there, the preview runs, and if we actually run it, the machine will move like that. So it is possible to put a whole lot of these in here, but it gets a little bit awkward because you also need to do a little bit of waiting in between, which is a little bit beyond the scope of this video, so we're not going to do that. You can also use new lines here, so if I put \n and then put another command, it will run them all in sequence. But what you're far better off doing is, instead of running a single command, you would run a command list. And a command list is one of these files that we've saved over here. So let's save this one because I have not actually saved it yet. But if I save this as, I think demo should be okay. Yeah. So now that tab is called demo, and if I run command list demo, we can preview it. Let's make this wait a little bit shorter, so 0.25 seconds there, and run that. Well, let's run it again because it was already over on the right hand side. So if we run it now, it'll go like that. And again, if I hit the F6 key on my keyboard, it runs, and also with that buttons view, we can run it from the button like that. So that could be useful sometimes, but what's really useful is being able to substitute some of these values here instead of being hard-coded. And we do that by using something called a dictionary, or in some languages this is called an associative array, and we pass that also to the function where we're running, calling this command list. So if I do this now, it's not going to change anything, but I can, inside that dictionary, I can say that the end point should be, so we're moving over to x140 at the moment. Let's move over to x200 instead, like that. And so instead of having a hard-coded 140, I change that to a sort of a Perl or a PHP looking variable like that, so it's $end. Now if I run that, you'll see it goes to 200 instead. And I want to repeat that. I think I can do this. So I'm not going to explain the await because there's a little bit too much to that, but the await basically makes it so that nothing will happen until this last trajectory result up here returns back as success. So it just makes sure that we don't flood the server with these run command lists all at once. So let's make this 140 here, and then 200, and it should run twice this time, like that. And then hopefully you can see how useful this is. You can put that in a loop, right? So it's going to go 80 and then 100 and then 140 and so on. So if I just hit F6 on my keyboard, so that stuff there would be the core of the movement related functionality as far as the script deals with it. We also have a bunch of functions that I'm just going to paste in here from my cheat sheet that let us interact and read and write with the other aspects of the weenyPRU, like the digital inputs and outputs, vacuum sensor, ADC sensor, load cell, and all that stuff. This is by no means all of them. I'm just giving you a little overview there. We can also interact with the workspace layout via script. So the workspace layout is the position of all these windows and which ones are open and which ones are closed. So let's say this layout here, I want to save that as, let's call it YouTube, because that's what we're doing right now. So we save that. And then I can load these other layouts, for example, none, is nothing. Oh, that camera's probably not supposed to be showing. Wait, did it just freeze? Oh, I know it freeze. Okay, just ignore that. That's a bug. But then we can go back to... Well, let me open up my script editor here. In my script here, we'll do it with script, right? So we'll say load workspace layout. And it was called YouTube, right? Right, so now if I hit F6, it brings me back to the layout I had before. Was this open? Did I have that open? I thought that was there. Hold on. Save layout. Alright, so now if we go layout none, hit the F6 key. There we go. That's what I was trying to show you. So of course, we're kind of running out of function keys here, but if we wanted to switch between layouts with the function keys, we could do it like this. None, and then say hi to event hooks, function keys. So F7 would be say hi to, which is actually going to be loading the none. So we can switch between those now with the function keys like that. So when you get all these windows all over the place, you really want to have some quick way to just sort of get them out of the way and look at different aspects of the program. So this is a convenient way to do that. Another couple of functions that can be quite handy are setMemoryNumber and setDBNumber. So that's like setMemoryNumber, and then we give it a name. So just call it my number, and then a value. So what this will do, it will just store this number in memory so that it will persist between runs of the script. But when you quit the program, it'll be gone. And then you can get that by get memory number, and you can also try have memory number to check if it exists. Oh, of course, these ones would not have the value itself. But just to show you what I mean, print get memory number like this. Sorry, okay. And then we want to say hi, run. So it's just putting into memory and then retrieving it. And if you want a number that does persist after the program has been closed down and restarted, you can do db instead of memory, and it's just going to give us the same result here, but the difference is that if I was to close this client down and restart it tomorrow, for example, this number would still be in the DB, but it should be. It just gives us the same result here. So this DB, what it's referring to there is the SQLite database. And the script does actually have full normal access to the database as well. So if we look at something called DB browser for SQLite, I'll just scroll this down a bit, you can see there DB browser for SQLite. So it's opened the same file that the PNP client is looking at there. It's called mypnp.db. I guess you could have different names for it. But this lets us see all the tables that exist in the database, and if we were to browse the data, let's look at the table called file, and we'll see, oh sorry, internal. I changed the name of these at some point. So internal file, and there should be one called demo here, and if we look at this, we'll see that this contains a little bit of text that we were working on before in our command list. So all this stuff is saved in an SQLite database. And let's have a look at one of these other tables here. And let's look at iomixer version 1.2 BOM. Now this was imported directly from a CSV file that was produced by EasyEDA, or the JLC PCB's PCB editor program. So I just dumped it straight into here by using the import function here, database from table from CSV file. So that's how this file got in there, but it's not in the format that I wanted it. The other file that we get from JLC PCB's export is this PNP one, I think. Yeah, so this one here lists up the components, what type they are, the location that they should go, X, Y, and there's also a rotation here as well. Now, using script, I was able to create this other one called job, which has everything from those two tables merged together in a format that I want. And I've added a column here called done, which as the job progresses through, my plan is, I haven't done this yet, but I'm planning to mark this as a 1 for each component that's done, so that you could stop and start the job in the middle and it wouldn't try and repeat a component that it's already placed. Now if we go back to the pick and place control, and I'll just show you the file that does this. It's called importing, I think. Yep. So I'm not really going to look at this in too much detail, but hopefully those of you who are familiar with SQL will see that we can do things like this. So there's a DB query which issues a query to this SQLite database, and we can do things like deleting rows. So here I'm just dumping a whole bunch of things that I didn't care about, like the headers mostly and the pads. And then we can do selects, and we can drop table. Should be create table somewhere down here too. Insert into. Here we go. So we've got create table. So using this script here, I was able to completely generate a new table in the format that I want to, just using a script like this. And as well as looking at those tables in this DB browser, we can also look at them here, although it's not quite as fully featured. If I open this panel here, we'll see we can only see the tables that are not internal. So over here we had some that are named internal something or other. So those are required for the PNP client itself to function properly. But for the ones that are not labeled internal something, we can see all of these here. So let's just look at the one I was talking about before, iomixer version 1.2 job. If I click on here, this window here will open, and we can see basically the same stuff that we saw in the DB browser view. And we can actually edit this. So if I wanted this, I don't know if I want to change these actually, but I'll put this to like 182, for example. Pretty sure that will be fine. And then I can save that like this, and it will get saved into the database. So I figured this was just a little bit easier than having to go over to this other editor every time. Some people might not be bothered to install this. It is cross-platform on Windows, Mac, and Linux, so it's not. I don't think it should be a huge problem for people to use this to edit data, but it's just a little bit more convenient, I think, if it's inside the PNP client program itself. Okay, I've mentioned overrides a few times without telling you what they are, so let's have a look at those. We can find them in the server window under the overrides tab. So an override is a very small, simple piece of logic that needs to run very fast, and it's going to be running continuously, like in the background. And as such, we don't have to fiddle with the settings of it very often. So we just set it up once in this panel, and then we give these instructions to the server, and then the server just runs this every 1,000th of a second. So these are very, very fast little pieces of logic. So a piece of logic might be something like, when vacuum sensor 0 is more than minus 30 kilopascals, set digital output 0 to high. And then as a higher priority, when vacuum sensor 0 is less than minus 35, set digital output 0 to low. So these two overrides together are going to maintain a constant or a target vacuum within my small reservoir of my machine. So if you saw my previous video about this, I have a large vacuum reservoir that's targeted to keep at minus 80 kilopascals, and then there's a smaller one on the desk closer to the machine that is trying to keep itself at minus 30 kilopascals. So these two overrides together are going to do that. And then down here we have another one that says when digital output 1 is high, set digital output 0 to low. So we're not going to do any vacuum replenishing between the reservoirs while digital output 1 is high, because digital output 1 is the output that opens the nozzle to pick up a component. So we don't want to be doing this replenishing up here while the machine is picking up a component and moving around with it. And to edit these, we can click on edit here. And so it's not just vacuum sensor, it's all these other things here. So we've got ADC input, load cell, vacuum, digital, blah, 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 motion axis. And then we want to also say whether it's less than or more than a certain value. And then we can add an action either for when that condition passes or for when it fails, like the negative or the opposite of that case. And we can have multiple actions down here. We want to add actions. We can have a whole bunch of them. And we just click done to get rid of that. So let's have a look at what these three overrides are doing together. To do that, we'll have to look at the plots window, where we're looking at the vacuum level, and it's at about minus 32 at the moment. And you can see that there's a fairly decent leak in this vacuum system somewhere. Might have to figure that out, but the fact that I have this regulating thing means that I don't have to worry too much about figuring it out. But anyway, when it gets to minus 30, maybe you could hear the little valve opening and closing just briefly there. So it opens up so that the large reservoir feeds into the small one until it gets to minus 35, and then it stops. Wow, that's quite a leak, isn't it? It's already back to minus 32. But the point is, I wasn't controlling that manually, and the client wasn't telling the server what to do. It knows what to do all the time, and it's a very fast reaction. If we come over here, I've got a little bit of code that will simulate what it might look like if the nozzle was to be open to vacuum just briefly for 0.2 seconds. And if I run that, I ran that in the middle of what it was trying to replenish, and as you can see, this is a higher priority, so that override, or the first two overrides, were abandoned. So instead of getting all the way to the bottom, I was able to stop it. And if I zoom out a bit and do this a whole bunch of times, you can see as soon as I stop doing my pick and place simulation, it's constantly trying to replenish itself down to -35 like that. But the point is, it doesn't replenish while it's picking. Okay, let's have a look at that other override, or the other sets of overrides down here. Now, this is not really what I made these overrides for, but it occurred to me that it could be useful for this. So let's have a look at this one. Override priority 3 says that when motion axis Y is less than 85, set digital output 3 to high, otherwise set digital output 3 to low. So motion axis Y is the front to back movement of the machine, and when it's less than 85, that means it's close to the front of the machine, 85 millimeters this is. And digital output 3 is the output that controls this LED ring by the bottom camera. But we also have override priorities 4 and 5, which are based on motion axis X, and they will turn digital output 3 off depending on whether it's more than or less than some values there. So let's see what that does. If I come over to my other little test command list here and run this, we'll see it goes over the camera and stops just for a little moment, and then it zips back across it on the way back. Now, my command list here does not contain any commands to turn this light off and on. It's all coming from the overrides, because it's very simple logic that most of the time when this nozzle comes over the camera, we want to look at something and we want to look at it with the lights on. Now, how are we turning that light on though? Because this is an RGB LED strip or ring, but we're controlling it with just a single digital output. Well, that digital output is actually connected to an iomixer, so this is getting a little bit outside the scope of this PNP client, but I'll just show you what it's doing. So the iomixer is reading or looking at this digital input here, and it's using that to multiply this color. So when this goes to 1 or 0, it's either going to turn the lights completely off or completely on. And the color is going to be depending on these three nodes here, which are set by default to 0.75 each, so that's going to be white. And then that's feeding into RGB LED indices 1 to 24, so there must be 24 LEDs on that ring. So just to clarify, there's no RGB LED facility or feature or capability in the PNP client itself. It's just relying on the iomixer to get these colors to change. Oh, did I say colors changing? Yes. Well, we can actually manipulate the values of these nodes here, because the iomixer can read information over a serial port. So you could send G-code or something like G-code to control the values of these nodes and override them. So that's what I'm doing, and let's just have a look at how we can interface with serial ports from the pick and place client. And if we look at serial here, we'll see a little window that detects what serial ports are available. The first one is the iomixer itself. This is not really a serial port in the traditional sense, but it shows up here because it's a virtual COM port. The serial port that I'm actually using to communicate is this one down here. It's just a regular FTDI adapter. And quite often these have a unique ID. This one, I'm not quite sure if it's unique or not, but this ID here is quite useful sometimes if you want to identify which particular device you're talking to, because sometimes when you plug these in, they come up on TTY USB 0, and if you have two of them, it might come up on TTY USB 1, which is a little bit awkward because it prevents you from using this as the identifier. So that's why I've gone to the trouble of making this little window so you can get all the information from each of these serial adapters, and if you click here, it'll copy this string to the clipboard so you can use it in your code. So that's what I've done here. That's why I have this little bit of code to try and find the particular serial port that I want to talk to, and we do get serial port by description like that, and then we open serial port with a certain baud rate, and then we can do things like this. So send serial will just send this text to that serial port, And the format of this text is not really important for this video, but this is the iomixer kind of format now. So S means set, node 1, and then V is the value. And nodes 5 and 6 are the other ones that we had there. So if we look at these, we have, it's node 1 for red, and then 5 and 6 for the green and the blue. That's why there's a 5 and a 6 there. And they're taking their values from the parameters given to this function, and then I have another function over here where I'm calling that 4 times with different parameters, and it's going to set the values to red, green, blue, and white, and it's waiting for half a second in between those. Now the last color is white, so if I run this here, it's going to take a couple of seconds to run. We don't see anything because the the nozzle's not over the light at the moment. So if I run this now, we get white because that's the last color. But if I was to, for example, put a return here and run that this time, now if I run this, we'll get a red light like that. And if I take that return out again and I run this, but I stop it there, so hitting escape will stop anything that's running will be stopped by hitting the escape key, kind of like LinuxCNC. Now if I run the script, we should see cycling between those colors every half a second until it gets to white. So we can go red, green, blue, white, and that's just a test of interfacing between this PNP client and the iomixer. I'm not suggesting that this is really something people would want to do. What this would really be useful for in the context of a pick and place machine, I think, is to control feeders. So if you have, say, 30 feeders or something, instead of using this format here, I've seen some Arduino-based feeder boards actually, where they accept some kind of a G-code text like this telling them which feeder to feed the component from. So if you have something like that, I think this system would be great to work along with that. Oh, I forgot to mention that the PNP client can also read a reply from the external device if the external device is one that can send a reply. So for example, I've altered my program on the iomixer a bit to add this node here, which is just a simple analog input, and this has become node number 7. And I have just a little potentiometer that's going in here to read, and if I show the values from that, we can see it's at 0.3, and if I turn it a little bit here, we'll get up to about 0.59 or something like that. So that's the values that are being produced by that. And over here on our pick and place thingy, I have a function called readAnalog, which is what we're going to be running there, and instead of just sending and not retrieving a return value from this function, I have done this here. So we've got serial reply, which is a special type of object that will receive the data from the reply if there is one, and we're putting it into this reply variable. We have an extra parameter at the end here, which is a regular expression, and if this matches, you can have multiple captured expressions inside here, and they'll each be recorded inside this reply object, which we're just going to print out here. And to do this, we do G, which is get, and then node 7. So if I run this, we'll see down here the result of that was OK. The string that was received, the full string, is OKN7. So this is the reply that the iomixer gives there. And then from that, we have ascertained that the values we received were a total of 1 value, and the value of that was 0.59. So if we put this in a loop and run it a few times, like this. So we're going to run that 10 times with 500 milliseconds in between. And then instead of printing out this reply all the time, I think I can do vals 0 maybe? See what that does. Yeah, so that should just print out the value only. And I'll run that again, and this time I'll turn the dial a little bit. Well, you can already see the values were different there, but let's clear that. And I'll run it while I'm turning the dial a bit. You can see the values are changing up to 1 and down to about 0-ish. So that's just to demonstrate that if your external device was capable of providing replies like this, then this PNP client can do something with them. Okay, let's have a look at probing. There are 3 types: digital, load cell, and vacuum sensor, and in order for any of them to work, you will need to have set them up appropriately in this server window under the probing tab. I think we looked at this a little bit before, so I'm going to just gloss over that. There's a section here where you can test your settings to see if everything's working, but I want to show how you can use this with script. So I'm just going to close that. And over here in the webcam, you can see, I'll just make this a bit bigger. you can see we have a load cell here and a clicky switch, and these have been set up so that when I push the clicky switch, we'll get one of the, I'm not sure which one it is over here, but one of these inputs should go green, like this, whichever one that was. And when I touch the load cell, we should see something happening on here. So you can see I've calibrated this so that the weight that we're looking at there is actually correct. So it's about 20 to 30 grams pressure that I was just applying. And then over here we're going to sense using the vacuum sensor method. We're going to sense when it touches this piece of MDF. So those are my 3 locations where we're going to check probing. And here's my script. The main part of it is this probe function, but just forget about that for right now. Look at these ones at the bottom where we have go to digital, go to load cell, and go to vacuum. And these use another function called clear move, which is not defined in this file. All of these files, by the way, are in the same scope. So any of these other functions, here's the clear move function there. They're all accessible from anywhere. So what this does is it raises the nozzle up to Z0, and then it moves horizontally to that XY position, and then it goes down again to that Z position. And then we're going to call probe, and we're going to pass what type of probe we want to do. It has to match the location we are. So if you go to the top of the load cell and you try and do a digital probe, well, that's not going to be very successful. Likewise, if you go over here and try to probe for a load cell, that's not going to work either. So this probe function, I'm just going to comment this out, or I'm just going to return without doing anything for starters. And I have these 3 functions here attached or triggered by my function key. So if I push F6, we go over to the clicky switch. F7 we go to the load cell, and then F8 we go back to there. So now if I take this return out, and I'll press F6 so that we go over and probe the clicky switch. And you can see down here in the printed output here, we've got finished probe result equals 1, which is success. And the height that it clicked the switch at was minus 10.5396 millimeters. So let's just look at this probe function a bit more. First we await, this is to make sure that the clear move part is finished. And then we call the probe function with the maximum depth, or the lowest Z position that it's allowed to probe down to. And then using the type that we passed from over here, one of these ones. Then we have to wait for that to finish, because this is actually done by the server. It's another one of these tasks that gets handed over to the server to execute. So we have to wait till it's finished, and then we get the result. And if the result was success, we print out the height, and then we just run a command mz0 to move up to z0 again. So let me run that again. Just take a note of that number, minus 10.5396, and see how close it is the next time. Okay, so it's about, I was going to say it's about the same. It's exactly the same. Now let's try the load cell, and I'll put the load cell graph over here so you can see what the load cell is sensing at the time. And you can see it does 2 approaches, so the second approach is much slower, like we did here. So it looks like 13.3796 was the result for the load cell. 13.3796 again. Alright, and then we'll go over to the MDF. So the way the vacuum, I think I mentioned this before, but the vacuum sensor just turns the vacuum, or opens the nozzle over and over, checking what the difference in vacuum pressure is between the start and the finish of when it closed it. So let's have a look at, I should have been showing you this. Let's try that again. So you can see each time it opens and closes the nozzle, the loss of pressure is a small amount. Well, actually no, sorry. Let me pause that. Let's have a look at this. So we lose relatively a large amount of pressure compared to that very last time where we only lost a little bit of pressure, and that's because the nozzle was touching against the MDF, so it was kind of sealed off and the air from outside wasn't able to go into the nozzle as quickly. It still went in there a little bit. You can see there's a little bit of pressure loss there. But basically the difference between the first set of open and closes and this last one is what it uses to decide that it's touched something. So the result for that was 24.3996 both times, so seems to be quite repeatable. Okay, let's take a look at some of the camera and vision related functions. I'm just going to do this here at my main desk because I don't need to be next to the machine for this. I just need a webcam, and with my webcam we're going to be looking at this brightly colored piece of cardboard, and then we're going to be looking at this not so brightly colored black cardboard box with some things stuck to it, and then we're going to have a look at some QR codes as well. So as I mentioned earlier in the video, the USB webcam parameters can be controlled by this little panel here, and we can also control them via script, or some of these things we can control via script. So that's what we're going to try now. And we have a function called setUSBCameraParams. The first parameter to this is the index of the camera. So this is the camera 0, as you see at the top of the window there. And just for this little demo, we're going to change it so that the focus is blurrier, the exposure is darker, and the saturation is set to 0, so that's like grayscale or black and white. And when we do that, we'll see that for the focus and the exposure, they'll switch away from being auto where they are at the moment, and they'll go into the manual mode. And then we're going to wait 3 seconds, and then we're going to set the parameters back to something pretty much like what we have already. So let's run that, and you'll see dark and blurry, grayscale, and then back to normal, and we've switched away from the auto stuff here. Now I want this auto stuff back on for the rest of what I'm doing here, so I'm just going to click these back on here myself. But that's how you can change the params at any time you like using script. The next little demo here, we have grabFrame, and then we save image. That should be pretty self-explanatory, I think. This is the name of the image to save to on disk. So if I change my function here to camera demo 2 and run that, where is my file here? Hold on a second. So that's this file here, and just to make sure it's actually doing that while I'm pushing the button, I'll put my fingers in the frame, and you can see every time I click, it's saving that file there. And we have a few other images here. This one in particular we'll see again in a minute. This is called tapeholes.png. This is one that I was using for testing something. So let's go over to this other tab where I have a bunch of functions here. Now these are for a slightly different purpose. So as we know, we have an entry function that we can specify, and then we can click run here, or we can attach this to like a function key or a GUI button or something to run it. We have also up in the top of this webcam window another entry function setting here. Now these are a little bit different in that they don't get executed by you clicking run on a button here. They get executed every time a webcam frame comes in. It will be processed by this function. So this is going to be running at 30 times per second. And we have a function here called VisionDemo1, and it's going to do load image tapeholes.png. That's the image that we just saw before. So if I click this, instead of seeing the live view, it's just going to override it with a fixed view. And this is quite useful if you're trying to debug a certain situation that's a little bit tricky to reproduce or whatever. If you can snap a photo of it at some point, you can just load it into here, and then all of your subsequent image pipeline or processing or whatever can be done on this instead of a live image. So that's quite useful. Vision Demo 2, let's have a look at this. So this is just showing how we can flip the frame. This FF both means vertical and horizontal. So if I run that, you'll see it's vertical and horizontal essentially means that the image is rotated 180 degrees. So still live, of course. So it's just going to be either that way or that way. Vision Demo 3, let's see, this is drawing things. So if you do this, we can see we can set the draw color. We can draw a couple of lines to make it cross here. It's a little bit hard to see there, maybe with this cross here in the middle of the screen. And then we change the color to a kind of an orange, and then we draw another line and a rectangle and a circle and a cross up in the top left. And then we draw some text. The text says loadcell raw, and then we're using this get loadcell function, which I forgot to mention before, but all of the stuff in the status panel here is accessible from script as well. So I'm just using the load cell value because this is the only one that's really changing at the moment. So you can see that value in the text changing there. Oh, by the way, at the top of the window here, we can see how long it takes to do this processing. So this processing time refers to however long it takes to do whatever's in this function. So the drawing of these graphical elements here at the moment is taking about 80 microseconds to do. And for this drawRect one here, you'll notice that instead of giving hard-coded values, we're using these get tweak values for W and H for the width and the height. So this one here, I can change the width and the height of that rectangle in the top left. And this just sort of shows that everything's happening live, it's updating 30 frames per second. So moving along, let's do Vision Demo 4. This is a blur, so let's try that. For blur, go. And as you can see there, it's blurred in the middle. And we have something called set vision window size as well. So I can change the size of the vision window, meaning the area that the vision vision processing is going to be applied to, like this. So you can see the blur only extends to as far as that. So this can help cut down on the processing time if you only need to process a small area in the center of the frame, which is quite common. And this draw window here is just drawing a border around it, because without the border sometimes it can be a little bit tricky to see where the edge of it is. On the kernel here, I can change the amount of blur too. So if I put this down to 0, it's actually not doing any blur at all. Or I can make it really blurry up there like that. But yeah, sometimes the window, like at the top of the window there, you can't really see where it is very well. So that's why I made this draw window function, so it's a little bit easier to see like that. All right, let's move on to Vision Demo 5, which is HSV threshold, or hue saturation variance threshold. So if we turn this one on, we'll see nothing changes at this point because the threshold is being given the entire range. So the first two parameters are here for the hue range that we're allowed to use, and then we've got saturation and variance, or sorry, not variance, value. It's value, but I keep saying variance for some reason, sorry. And in the case of the latter two, they go from 0 to 255. So this means every pixel is okay to keep. And when we don't keep a pixel, it's just going to be set to black. Now, for those who are not familiar with what HSV colors are, let's have a little look at this thing that I stole from Wikipedia. Basically, value is similar to a brightness in that if the value is 0, it's going to be black. A high value is going to be not white, but whatever color it would be if it wasn't, completely dark. Saturation is a value meaning how much color there is in the pixel rather. So at the center of this wheel here, it would be white, and at the outside it would be full color, like full red or full green or whatever. And then the hue defines whether it's red or green or blue or whatever. And this is a bit of an awkward one because it kind of goes around in a circle. So it starts at 0 and then it goes around to, in my case, it goes around to 255, and then it jumps back to 0 again. So it's kind of annoying that you can't just set a minimum and a maximum value. You have to set a center point and then a range. Think of it like you're cutting a slice of pizza, and the center point is what location around the pizza you want to cut from, and then the range is how wide your slice of pizza will be. So that's the center and the range for the hue that we're going to look at in a second. So the defaults here are 0 for the center of the hue, and then 128 each side of that, which means that the entire range of hues is going to be covered, and these are 0 to 255. So we're going to allow every pixel to get through, which is why nothing changed. But let's change it so that for the value, we only accept high value pixels, meaning kind of bright ones. So if we do this, everything that was not bright enough to get past that threshold is going to be set to black. And again, this is my window is taking effect here as well. Hope that makes sense. And let's put that back to 0, and then we'll try the saturation, and we'll take only high saturation pixels, meaning anything that has a lot of color in it. So if something's kind of like a black and white, like black, white, or gray, in that sort of grayscale, then those pixels will be dropped. So when we do this, let me just zoom in a little bit here. Let's zoom into about there. So if I turn this off and on, you can see that the pixels that we're dropping is anything that didn't have a whole lot of color in it. So anything that's black obviously gets dropped. Interestingly, the white gets dropped as well. So you can see that all the white bits go away. And anything that was gray, like these, in between each line of these feathers here, there's actually a gray line. So that's why these bits in here got dropped as well. So that's saturation. And then for the hue, I'm going to change it to this one here, which has, for the hue, I'm going to take the hue center and hue range from these sliders here. So we've got center and range, and if I set this here now, what happened? Did that work? Oh, sorry, I had this turned off. got to keep this checkbox on if you want the functions to be applied. All right, so we've got hue center here now, and then hue range. And as I move the center, you'll see that different selections of color are being kept, and different selections are being deleted or removed. And it looks a bit haphazard as I move this. You might think, what the heck is going on? But it makes a little bit more sense if we use one of these color wheels, which I have on my tablet here, just Wikipedia again. And this time when I move the hue center, it should be a little bit clearer what's going on. So we're just taking a slice out of that pizza, if you like, and the hue center says which part of it we're going to take from. The hue range, I think there's a bit of a bug with this hue range at the moment, because if I set that all the way to full, it takes the whole pizza, which is what we expect. But when I set it back down to 0, it's taking half of the pizza still. So I think what this should be doing is taking none of the pizza. So there's a bit of a bug there at the moment. I'll have to figure out what's going on with that. But I think you can get the idea of what this HSV threshold does. So let me take this away now, and oops, put this back up. And let's move on to our next demo, which is Vision Demo 6. I'm actually going to put a return here. We don't want to do the rest of that. So let's just do the first part of it, and we'll turn that on. And then we'll see what we're getting here is basically we're getting all of the white bits, or yeah, pretty much. And the way we're doing that is by setting thresholds on the saturation, so that only very low saturation pixels can make it through the filter. So that's going to be grayscale kind of pixels. And then for the value, we're taking only pixels that are high value. So that's going to be basically what this is going to do, is let through only white pixels, or pixels that are very close to white. So if I turn this off and on a bit, you'll see we're just keeping everything that was white or nearly white. And then the point of this, though, was for the next step to find blobs. So this quick blob function is going to find something called blobs. Now, blob is just a group of pixels that are all together touching each other. So it's like an island, you could say. So this N, the letter N here, is a blob, and then the letter E is a blob, and so on. And so if we do call this function quick blob and then set the color to purple, and then we're just going to draw a rectangle around all of the blobs that we found. It looks like this, and I'll just make that a bit bigger so you can see all the blobs showing up there. And of course, if I move this around, they're all being found in real time. And if I get my other piece of stuff over here that we're going to look at, maybe it'll become a little bit clearer why we might want to do this or where this is going. So we've got some blobs on there, a little bit out of focus, but that's all right. So let's move on to Vision Demo 7. What was this? I've got so many on. Oh, convex hull. Yeah, okay, so this is quite interesting. If you know what a convex hull is, you should be able to see one there in the video. And again, it's not very useful on the letters, but if we make this window a bit smaller, and then we bring this in again, it might be a little bit more sensible. So we can find a convex hull around that shape there, and around that, and then around this, and around these maybe. This one's a little bit tricky. And like this. Oops. I haven't set up the exposure very well for this, so it's finding, the reason it's jittering around is it's finding brightly colored pixels outside the part that I'm trying to look at. The convex hull in itself is not particularly useful, but this next thing called a min area rect is quite useful. So let's look at the next demo, and we'll run that. Get my little thing up here again, and now we can see that this is kind of the end goal of this vision, is to find, or at least for bottom vision, we want to find again, it's jumping. I need to make this window a bit smaller, do I? Or bigger maybe, or I just need to hold it still properly. Okay, there we go. So for bottom vision, what you want to do is figure out where the component is and how it's rotated. So that's what this min area rect is quite good at doing, like that. So you can see we found the rotation, the location and the rotation of this thing. And ooh, that's a bit jumpy. Unfortunately, I glued these on here with UHU-POR, and even where there's just a tiny little bit of UHU-POR that got stuck over the side of it, it's finding that, unfortunately. So that's that one. That one, you can see the rotation, whoops, is being found. It's quite blurry there, but it's still finding it. That one, we have the rotation. It would be better if these were focused a bit nicer, but you can see how it's working. So those mini area rects are very important, I gather. There's a little bit more work to do on some of these features. For example, you can see at the moment it's still finding a rectangle there. So what it really should be doing is trying to figure out if there's anything sensible that it's actually looking at instead of just always returning a rectangle. So, you know, it's a work in progress. Okay, so Vision Demo 9. This one should be pretty self-explanatory. I'll just run it and let you see what it does. Nothing right there, but we put these in the frame. We'll see. We can find some QR codes, so we get the location and the corner points of these, and of course also the text that they contain. Got a few more here. Let's look at these ones. Bunch of numbers. URL. These are just some that I found in a quick Google search. The one in the top left here is actually a malformed one, I think. So it's okay that that one's not detected. And what's this? Scanned it AG. You can see where I got that one. And then I think this is one that I generated. The library that I'm using to detect these QR codes lets you generate them as well. So this is one that I generated with the library. My nice text. Okay, so that's all very well for looking at things in this webcam view. But of course you're going to want to use the results of what you found in your script somehow. And the way we can do that is basically we just do the same stuff here, but in front of that we have to do grabFrame, right? So this grabFrame means that we're going to get the latest picture from the camera before we do the vision processing. So let's see, for example here, well, it's the same as what we did before with saving the image, but I'm just making the point here that all of the vision processing that we did will be saved into that image as well. So let's put that back to 6 and make the window a bit bigger. So this is the one where we had the blobs made from the letters. And if I set this to camera demo 3 now, and I'll just put this over here and we'll look at that file again. And we'll run the script. So you can see that all of the vision processing stuff is written into that frame as well, so you can save it for future reference. Oh, I forgot to mention also, one thing about this display here is that everything's gone black. So we can't see what was there before. Let's say we come back to this another time and we want to figure out what was going on here. It's just black, so we can't see it, right? But we can do RGB copy, and then after the thing's done, we can do RGB overlay. So it's like we're taking a backup of the RGB frame, and then we can put it back on with a transparency of, in this case, let's try 0.5. And that will give us this kind of a result here. So it's a little bit dark, but we can still at least see what was going on in that picture. And of course we can do that in the live frame as well. So let's try that. All right, that's what I wanted to do. Okay, so now we can see basically what we saw before, except instead of having complete black in the background, we can actually see what's going on. So that's quite a bit more useful sometimes. Now to finish off this little demo, let's show an example of using some of the results from one of these functions to do something, basically, because the whole idea with this system is that you're going to look at something with the camera, and based on what the camera sees, you're going to make a decision about it, right? So let's do that. I'm going to uncomment this function, and in here we grab the frame, and then we do vision demo 6, which is this one here that we're looking at right now. But we're trying to get an integer value back from that function, but this is a void function at the moment. It returns a void. Unfortunately, all of these functions that we specify as the entry function, at the moment they have to be a void, like they have to return a void. But it's a little bit inconvenient, so I think in the future I might make it so that basically they can return any kind of a value. See, it's void here, but what I want is to return an integer, and we're going to return the number of blobs that are seen. So there's about 20, if I had my finger out of the way, there's about 20 or so blobs in there. So when we come back here, so if there's more than 10 blobs, well, it's going to print the number of blobs down here. And then if there's more than 10 blobs, it's going to do notify many blobs found with the success status. Otherwise, it's going to do notify a few blobs found with an error status. So this notify will just show a little notification in the top right of the screen. So keep your eye on there when I click the button. Oops, let's set that to 4. And unfortunately, it's behind there. Hold on, let me try it again. All right, so it says many blobs found because there's more than 10. If I cover this up with something, it should be less than 10 if I try this again. Now it says few blobs found. Many, few. This one's behind there now. What's going on? Hang on. Few, many, few. Keeps going behind. Okay, so I have to figure out why those go behind. That's a bit annoying. But anyway, you can see that based on what the camera sees, we can make some sort of a decision. Like this. It's the whole point of computer vision, isn't it? Alright, let's see how we can use these features to do something useful in the context of actually looking at a PCB. So I've got 2 cameras here now. This is the one that we had before, just looking at the machine externally. And then the one at the top is the top camera. It's black because the light is off and it's using a very low exposure, but I have a button here where I can turn the light on and off, like that. So I'll turn that on and I'll scroll down here or jog down here so that we can see the board. This is one of my iomixer boards. And the bottom left corner here we can see there's a fiducial. And if I move away from the fiducial a bit, you'll see that it has a sort of a browny circle around the shinier solder pad in the middle. And as I move across here, you'll see that the browny part goes to black, and that's because I'm using the HSV threshold to delete or to drop all of those pixels. And then I'm also doing a little bit of blob detection. Hopefully you can see there's a purple circle around the blob or the fiducial in the middle with a purple cross in it, and that's because we are currently looking at or we're applying the function view fiducial blob to this frame as we're looking at it, and it's this function here. So it has flip frame. I think we saw most of this stuff before. Find some blobs, draw a cross here and so on, so we don't really need to look at that too much. But basically the idea is we want to find out where in the frame this little fiducial is. This is a 1mm fiducial, by the way, so it's quite small. And what we'd like the machine to do is to center itself over the top of that blob so that the machine position will be the same position as the blob, or at least will be directly centered on it in the camera. And to do that, I have a function called center fiducial, which I'm not going to explain too much, but basically we've got this function called nudge towards fiducial, and what that will do is it will look at the closest blob to the center of the camera frame, which is, hopefully there's only going to be one. There may be more than one, but if there's more than one, we'll just go to the closest one, and we'll just move approximately halfway towards it, and we'll do that up to a total of, I think, 15 times, and yeah, 15 there. And if we get close enough, I think within 1 pixel, yeah, there we go. If we get to within 1 pixel of the destination like that, we consider it a success. And I have a function here that I can call just as a quick demo of that. It's just going to call center fiducial. So I'll put that in here and run that. And you'll see it sort of twiddles around until it gets to where it thinks it's right on top of the fiducial, which it actually is. It's right on top of the purple cross has now disappeared, so that's pretty good. And we actually have some other fiducials on this board. If we look over here in the other corners, or not quite in the corner, but it's over here, there's one. And in the same way, you can see we've got a blob there. We actually have another blob up there, but those are not going to be a problem because they're too far away from the center. And there's one up on this corner as well there. There's actually a 4th fiducial, but at the moment it's covered up by this USB plug, so we can't use that. But we really only need 3 fiducials, and what we're trying to do here is generate or calculate some sort of an affine transform that we can use to transform positions in the design coordinates, or my CAD, or whatever you call it, you know, this thing, and figure out what they're going to be in machine coordinates for all of the components that we need to place. And so we do that by looking at the 3 fiducials and doing some calculations. And so if we have a look at this fiducial here, we'll see that it is 1.905 millimeters and 3.048. This is the position XY location of this in design coordinates. But if we look back here, we'll see that the machine is at about, well, what is it, 30-ish and 250. So we need to figure out a mapping between those coordinates. And normally we'd read in those values from a database, which I'll show you how we can do that in a minute. But just for this first little step, I've hard-coded them. So we've got an XY position for each of my 3 fiducials, and we're putting those into an array. And oh, we're also, before we start, we're turning the top light on if it wasn't already. And then we're setting the USB camera params to get the lighting right and so on. Interestingly here, I'm not hard coding the index for the camera. So before I had a 0 here because I wanted to use camera 0, but now camera 0, rather annoyingly, is this one. And sometimes when you plug the cameras in and take them out and plug them in again, they end up in a different order if you have multiple cameras, that is. If you only have one camera, it's always going to be 0. But what's happened here is my camera 0 is the one at the bottom, and this one at the top is camera 1. And I could just hard code this and put a 1 in here, but it's a little bit more useful if you can use this function here called get USB camera index by hash. And hash is just a little bit of a string that's formed out of the vendor ID and product ID. These are sort of USB constants, and you can see my 2 cameras here with all the information. And the bottom one here, index 1, has this hash 32E4 as part of it. You just need part of it there, so that's what I'm using to make sure that I set the USB camera parameters on the top camera instead of the other one. If the 2 cameras that you're using, or the 3 cameras or whatever, if they all have the same product ID and vendor ID, you can't do this, but the 2 cameras that I'm using right now, they are different IDs, so we can do that. And this get USB camera by index by hash, we also need to do that when we're using grabFrame. So this grabFrame function down here, we saw this before, but I wasn't using any parameters for it, and now I have to give the number 1 or else use this hash to get the right camera. Anyway, so let's just run this and see what it does. It's called run fids, so let's put that in here. Oops, like that, and we'll run it. So it's gonna repeat what we just saw, but it's gonna do it 3 times. And then it's going to go around one more time, just jumping directly to the position of each of those, just so that we can confirm that we got the position correct in the first time. And then it's going to scoot to the back a little bit, and it's going to turn the light off. And you can see in the printout down here, whoops, we've found these locations for the 3 fiducials that we're looking for. The X coordinate is not important, by the way. We're just using 2D values, so this is printing out a 3D vector, but just ignore the Z values. And that function was also doing a few other things, and one of them is this setMemoryNumber. So as we saw before, this just sets a number in memory and gives it a name. So for example, we're looping through here 3 times. I is going to be changing from 0 to 1 to 2. So the names of these numbers in memory are going to be fidx0, fidy0, and so on. And it's just storing the X and Y positions of the fiducials. And we also have a function called setMemoryString, which I didn't show you before, but you can figure out what it does from the name, hopefully. And we're just going to put a string in memory with the name label, and the value of the string is just a comma-separated XY value of the fiducial positions. And the reason that we're putting that in memory is because this is a handy way to pass information from these type of scripts that we trigger by clicking run manually, and these other scripts over here that are running 30 times a second from the webcam. So if I change this to something else, I have one called thick crosshair, which shows, yep, a thick crosshair, but it's also going to show some text in the bottom right quadrant of this crosshair the second time that this fiducial check goes around and looks at each of the 3 fiducials. So if I run this again now, we don't see the text just yet, but the second time, from now on, we see the text. It's a little bit hard to see with the contrast. I think I need to make it so that the text has a darker background or something so that we can see it better. So now that we've figured out the positions of those fiducials and we've stored them in memory, we need to do a little bit of matrix calculation to come up with an affine transform between those 3 positions and the 3 positions of the fiducials in the design. So of course they are here as well. So there's one there, and then there's one there, and then there's one up there. And to do that, I asked my friend ChatGPT if ChatGPT could do this for me, and it said, yeah, no problem. And it also said, AngelScript is no problem either. So that's nice. So this function here, I just copy and pasted that directly out of ChatGPT. Thank you very much. So what we're going to do is we're going to take as the input for the mapping the positions of those fiducials in the design, or the design coordinates. That's these 1.9 and 3.0 ones that we saw just a little bit earlier. We've got 3 fiducial positions there, and we want to map those onto the numbers that we put in memory that were called fidx0 and fidy0, like that. And so I didn't write this part myself either, but I just put these ones in here as the destination for the mapping. And so this function is going to do that calculation, then it's going to print them out so we can see what they were. And then as the output of this, or the goal, is to put another bunch of numbers in memory like this. And these are the coefficients of the matrix that's going to do the transformation. So if I actually look at the ChatGPT page, so this matrix here is what we're trying to come up with at this point. A little bit beyond the scope of this video perhaps. But anyway, that's what that setMemoryNumber is going to do. Now this has a little bit of a habit of crashing because I think it might be a bug in AngelScript. It doesn't seem to like these arrays of floats like that. And rather annoyingly, it runs once, but if you run it again, it tends to crash. And this is my second take of making this little piece of video, so there's a pretty good chance this is not going to work, but fingers crossed. Let's clear that. Please don't crash. Good. Alright, so we can see that the scale of the transform is pretty much bang on 1, which is good because that means the machine is set up correctly so that when it moves 1 millimeter, or when it thinks it's moving 1 millimeter, it is actually moving 1 millimeter in real world. So that's good that that's 1. Then we can see the 6 coefficients of that matrix there. We don't really need to look at that, but it's just nice to see that it's all working. Now based on those 6 coefficients, we have this function that we can use called apply affine transform, and this takes a vec3, but again we're only using the x and y positions, so we're just ignoring the z, so we're setting it to 0 every time. But basically we use that matrix to transform that value into so that value is going to be the design coordinates, and then the return value is going to be the machine position for that component or that coordinate. And then we have a function called test iomixer, which is going to go through a bunch of positions, and it's going to call this apply affine transform on all of them. And then it's going to do clear move. I'm not sure if I showed you this before, but clear move, basically it just lifts the nozzle up and then it moves to that XY position just to make sure the nozzle doesn't hit anything. And then it's going to wait 1 second. So we're going to go around and look at all of the components for 1 second. There's a bit of a problem though. The first part of this function has database query, and you can see it's got some SQL here, so select blah 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 from this table where name is not like fiducial and so on. But if I look at my database tables here, we don't have anything for the iomixer yet. If I refresh this, nope, no iomixer. And that's because I wanted to show how you can get this information into the pick and place controller from, in my case I'm using EasyEDA, so that's what my import script is going to work on. But basically you come here and you go export BOM, and then you click export BOM there, and that will save a CSV file to your computer. And then you do export pick and place file, and then you do export again, and same thing, you get another CSV file. And then what I'm using to get those into my SQLite database is this DB browser for SQLite program. Let's put that there like that. And we do this by importing table from CSV file, and we do BOM first. Either way is fine. And I need to change the name of this table to something specific that's going to match up with my script. So it's iomixer version 1.3 BOM. Okay. And then we need to do that again for the pick and place table, this one. So iomixer version 1.3 PNP this time. Let's get rid of that stuff at the beginning. Oh, this needs to be an underbar too, right? Yeah, that's right, so that's okay. So we've got a couple more tables here now, and if we browse the data just to check that we got that right, iomixer, where is it? So that's the BOM, and then we've got the PNP stuff there. So if we go back here and refresh, Oh, wait a minute. I always forget this. You have to write the changes from this app so that any other application that's using the database will see the changes. So now I can refresh here. Okay, so we've got iomixer version 1.3, BOM and PNP, but I still need to make those or merge those into a table that's in the format that I want to use more conveniently, and that's where this importing script comes in. I think I showed you this a little bit before. It drops a lot of rows that we're not interested in, then it creates a new table from those two, does a bunch of inserts and stuff. And up here I've set the name of the table to work from or with to that prefix that I had there before, so iomixer version 1.3. And I'll just make this a little bit bigger so you can see what it does. And it's called test import, even though it's working quite well. For some reason it's still called test. That's alright. Run. So a little bit of debugging output there just to see what was in those tables, and it takes a little bit of time there, but hopefully at the end it says import was a success, and you can see some of the inserts that it was doing there. And if we go back to the DB tables thing here and refresh, we'll have another, well, there's actually another two, but mainly it's this iomixer version 1.3 job that I'm interested in. So this is a little bit more of a succinct version of that information. It just has the name and the part ID, the X and Y position, the rotation. There's a couple of other columns that I'm not sure what I'm going to do with. So now, if we go back to this test iomixer function, now this database query, where we select that stuff, will work. And so we get a DB result object called job, and that has a number of rows in it, so we can figure out how many rows it has, and then for each row, we can look at the columns in that row like this. So we have part is the row, and then column is the function that retrieves column X, and we're assigning that to a float there, so we get a position. And we're also setting a memory string here. So again, the purpose of setting a memory string is so that we can show some text over here underneath this crosshair while it's moving around, and the text is going to show us the part name and a new line, and then the degrees of rotation that that part should be placed at. Alright, well that's enough waffling. Let's turn the top light on and we'll run this one. It's called test. It's called test iomixer, right? Omixer. Alright, let's run. Hope it works. Okay, it works. Good. So it's just jumping around there, and again the text is a little bit hard to read, but you can see hopefully that it's changing to the part name or part ID or whatever for each one of those parts. That's just the LCSC, is it? The IDs that JLC PCB uses. And they're all, the degrees are all multiples of 90, which is a bit boring, but I mean you can at least see that it's changing it sometimes. Yeah, so this is just to confirm that the machine has found the board, knows where everything is, knows the parts that need to go in each place, and the rotations as well. It should be just about done. Towards the end it does all these larger components like that. There we go, done. Okay, it's the next day now, and while I was editing some of the video that you just watched, it occurred to me that I didn't really test this Affine transform very well, because we're only looking at a transform that's it's almost an identity transform. It doesn't really change much. So what we should do to test this a bit better is rotate the board. And I've fiddled around with my scripts and I've added some buttons here. So what we're going to do now is we're going to manually jog to each fiducial position and then push one of these buttons here as appropriate. So for example, we'll go to about here, say, and then we'll push fiducial 0, and it will find, or it will center itself on fiducial 0, and it will put that in memory. And then we'll go over here until we find this one, and we'll do fiducial 1 for that one. And you can see when it finds it, it puts a little bit of text there to say where it was, and then fiducial 2 is up here like this. Fiducial 2. And then just as a check to make sure that we've got them where we thought we had them, we'll do visit fiducials like that. Looks alright. And then we'll do calculate affine, which I've already done. like I say, I don't want to run that one too much because it has a tendency to crash at the moment. So I'm just going to skip that, but it's already in memory and done. And then I have a button called Visit iomixer Parts, which will do what we saw just before, but it's triggered from a button instead. Oh, and I've also changed it so that the cross, I haven't actually tried this myself yet, so I hope it works, but when we rotate the board, this green cross now, instead of being fixed in the camera frame, is always horizontal and vertical. This green cross should rotate to whatever the degrees say there. So let me go and turn this board around a little bit, and hopefully, let's put it like about there. And hopefully, like I say, I haven't tried this yet, so I'm as curious as you to see what's going to happen. But in theory, we should just be able to do what we just did there. Whoops. Back up here a bit like that. Fiducial 0. Fiducial 1 should be about, oops, jogging speed is a little bit quick here. Fiducial 1. Fiducial 2 is up here. Hopefully we get all those right, and then we can just visit them just to check. And then we can do calculate Affine. Please don't crash. Looks like it's okay. Now, does this work? Visit iomixer parts. Okay, it works. Well, the position works. Looks like the rotation is reversed. It looks like. So hang on a minute. So I'm just going to put a minus here and then bracket around all that other stuff. Visit iomixer parts again. That's better. Nice. Okay, it works. Alright, well, the rest of that's just going to be the same. But the point is, the affine transform calculation works properly, so we know what rotation those parts should be placed at as well. Okay, I set up a little pretending job so that we can see what a real job might look like if it was running. The nozzle is going to come over to the left, and it's going to pretend to pick up a part from some invisible feeders over here. Each time it comes over, it's going to move along 5mm just so that it doesn't pick up from the exact same location every time. And then it's going to come over the bottom camera, and we'll be able to see the nozzle in the bottom camera there. And then it's going to go back over the PCB, and we'll see that the same as we had in the top view there. And then this view, of course, we can look at it from the outside. I managed to get 3 webcams showing all at the same time. It was a bit of a struggle. I've seen in the OpenPNP discussions that having more than 2 webcams in a USB hub can be problematic, and sure enough, it was kind of problematic. You can see all the info for them here, and I found that if I opened them in the wrong order, some of them would either just stay completely black or they'd be choppy and slow or whatever. But just by chance, I stumbled across an order which I could open them in which they're all staying open and functioning, so I hope it holds out. It doesn't really matter that you can't have 3 cameras open. You really only need the 2 for the top and the bottom camera. This one here is just for my convenience while I'm making this video, so that I don't have to record it separately and then edit it together while I'm editing the video. Anyway, let's run this, and we're running at about quarter or about third speed at the moment, just so you can see what happens. So we go over there, pick something up, look at it, place it on the board. And it's just going to do that for all of the parts over and over. But we can speed it up, and I found before that there's a bit of a problem if I try and grab this slider and drag it with my mouse to the end. Every time the mouse moves, it sends a message to the server, which is okay if there's nothing else happening, but in the middle of some fast movements, seems to cause the machine to stutter a little bit, which I'm not quite sure why, but in future I think I might make it so that instead of sending a message every time the mouse moves, it's just going to send the message when you let go of the slider. But for today I'm just going to click it like this so that I'm not actually sliding it, I'm just clicking it. So let's put it up to full speed. And hopefully in the future, someday, we'll see this doing actual work at this speed. This is about as fast as this machine can comfortably go, I think. Let's see what speed this is. Oh, you can see I was already looking at it. Let's look at it again. So the speeds are going up to 800 or so. That's pretty good actually. The longer movements, as I mentioned earlier, the longer movements are the only time you get a chance to get a lot of speed. So it looks like positive X and positive Y are going quite fast sometimes. So that's positive X would be that one. The positive Y is the one from the camera going up there. So those are the longest distances, I guess. Anyway, I don't think we need to watch all of this. This video is getting quite long, and I always say that, but this time it's really true, isn't it? By the way, if we use the preview button here instead of the run button, we can see a preview. Well, we've already seen this job now, but if we wanted to see what it looked like before we run it, we could use this, and you can see the little preview nozzle flying around there. And I could have sworn that I made this output the overall time that the run would take down here in this little output panel, but it doesn't seem to be showing it at the moment, so I'll have to look into that. It is telling us how long the script itself took to run, which is about 85 milliseconds, but that's not particularly useful. And as I said earlier in the video, I did a simulation of whether using a single nozzle or a double nozzle would be much different time-wise, and that's what I have on my preview board 1, preview board 2 buttons here. So if I click this one, you'll see a little bit more carefully constructed simulation. So it's going over the bottom camera there, and it's placing some items on the demo board. And this one here is what it would look like if it was doing it with 2 nozzles, and it's also simulating a flyover camera. So you can see it's going to one side of the bottom camera here, and then it's flying over the top. So like that, maybe you can see like that. And it's simulating one of those seesaw kind of nozzles, seesaw kind of head. So you can see sometimes it's going down to pick up a part, but then it's going over a little bit and up. And so the idea is that when one nozzle goes up, the other one goes down. So what would really be happening is the second nozzle would be picking something up from, say, about here. So I guess you could use this. It's only 4 axes in the software, but you could sort of cheese it a little bit like that in order to get a dual nozzle setup, provided that you could have the same rotation for both of your nozzles at the same time, which might not work out, but I don't know. I think you could probably do that actually. But anyway, yeah, so the previews like this, they should be outputting the total time that it takes, but I'll have to look into why they're not.
Just when I thought I was done with this video, it occurred to me that it would be an awful shame to have made a 2-hour video about a supposed pick-and-place machine and not even once showing it picking or placing anything. So that's what I'm going to try here. Unfortunately, all my iomixer's borders are already populated like that, so I can't really use those. In place of a bare board, I just printed out this piece of paper with it's the top layer of the iomixer circuit. And I only have these crappy things that I bought off Banggood about 5 years ago for some unknown reason. So I've just stuck one of those on there, and it's 0805s. And there's only 4 0805 components, so we're just going to place those on there.
So I won't bore you with all the details of the script. I'll just point out a couple of points where it's different. So in our database query, we have a clause where we say where the part is a certain part ID. And then we have a dictionary with a bunch of parameters that we're going to pass to the command list. So that's basically the XYZR of the pickup location and then the XYZR of the place location. And then we pass those all to the command list, which is over here in the green one. And so you can see where the substitutions are being made there. So one command list is going to be run on the server in one go. That's how it can be nice and fast. And over here, let's have a look at a few things. I've added a couple of what have we got here? Let's see. So let me just do a little bit of jogging so you can see what's going on with the tape. Let's jog over here. So in the same way that we found fiducials for the board, we're going to do tape hole 0 like this, and it's going to center itself on that tape hole and record the position. And then we go up to the top and do the same thing up there. Well, we could go all the way up, but I'm just going up to where there's the last component there, and that's tape hole 1. And then just to check that we got that right, we can do visit tape holes like that, and we can visit parts to make sure that the position of the parts is being calculated properly, like that. And then the fiducials for the board I've already done. The only thing I had to change here is that the HSV threshold is now looking for a darker spot instead of a lighter spot. So I've just reversed that essentially. And that's about it. So let me just run this. Oh, let's just have a look at the locations where these parts are going to go so that we're a little bit familiar with them. So it's there, 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 and there.
So the parts seem to be okay. A little bit hard to see there, sorry, everything's black and white. Hopefully you can see those parts are in the right location. Where's the other one? Last one is up there. Looks good to me. Yeah, nice.
By the way, I do have a little bit of script to calibrate the nozzle, so that's what this looks like if I run that. And we're looking at the thresholded picture here, but if I turn that off, you'll see it's just the nozzle. And we're just using the fact that the black, or the center of the nozzle, is very dark, and we're highlighting that with our threshold. And all this is doing is, well, it's already finished. Oh no, not quite finished. It just centers itself on the nozzle at 4 different rotations. It centers itself on the hole, I should say, and then it averages the position of that to get a rough center of rotation for the true location of the center as the nozzle rotates. And it works reasonably well. I have this check nozzle button here which I can click, and what that's supposed to do is it will move to the center of rotation location, and then it will rotate left and right 180 degrees each way. And ideally this center of this yellow cross here will make a circle around the green cross to show that we're circling around the center of the camera frame. So if I click this, it's actually a little bit quick. You can see that it's not quite right this time. I'll slow that down like so we can actually see it. So the yellow one should evenly be moving around the green one. I'll see if I can get it a bit better, run it again. This is just something I threw together fairly quickly. I haven't really polished it very much. I'm not even sure if this is really a good way to do it. Seems like it might be right, but this is not how OpenPNP does it, so that indicates something, doesn't it? Alright, now let's check it again. That's slightly better, but still for some reason it's a little bit off, isn't it? So I'm not going to use the bottom vision to correct the position of the part before it's placed. That's a little bit too tricky that I can be bothered with right now, and this video has taken a god awful long time to make already. But what I can do is just show you how we can find the min area rect from one of those resistors while it's over the camera. And you'll see I've got load image here, so if I click on there to load that in, this is just loading a static image in from disk. And you can see we've found the min area rect of one of these 0805 resistors. Unfortunately, it looks like there's a little bit of a shiny edge on the nozzle, the lip of the nozzle, so we've got a couple of white pixels there which are interfering with my rect. But anyway, when there is a rect in the frame, it's going to be spewing out found rect at whatever the location was and the angle. So let's see what that looks like when we actually run it. I'll take this load image away, like that. And then if we run the job, let me set this back to I set this to 1 part so I could take that photo, but we want 4 parts here, right? So let's run that again. So you can see the script is showing the location of that resistor when it's over the nozzle, when it's over the camera rather. And unfortunately I'm going to have to deal with the pixels that show up there, because you can see while it was, even though the resistor wasn't moving or anything, we're getting slightly different values because that pixel was sometimes showing and sometimes it wasn't. Okay, well that's all I have to show you as far as this machine goes. There's just a couple more things I wanted to talk about, and the first is that I feel I owe a huge debt of gratitude to all these libraries that I've made use of in making this thing. There's no way in the world that one person could come this far in what was essentially about 6 months initially. The first sort of February to August of last year was the bulk of the work that I spent on this. There's no way I could have done this without an immense amount of work done by other people and made available for free here. And I just thought I'd give a shout out to these libraries that I've used. So we have Dear IMGUI, that's the GUI interface, and IMPlot is kind of an extension to that. That was what I was using to display those nice little graphs. SQLite obviously is the database. libUVC is what we're using to access the webcam data streams. libAssetImporter is for loading and rendering 3D models. That was what I was using to display my machine as a 3D view. ZeroMQ is a networking library that makes it quite easy to publish a subscriber stream of information, and it also has request and response type interactions as well. AngelScript, I think we know all about that now. Z-Crossing, I think is how you say that one, and that's for reading and writing actually QR codes. Native File Dialog is a nice little GitHub repo I discovered that has some code that makes it pretty easy to set up, open and save file dialogues. And libSerialPort, obviously that's for reading and writing from a serial port. So a huge thank you to anyone who worked on any of that stuff. I really do feel like I'm standing on the shoulders of giants, as they say. And the last thing to talk about is obviously where can you get this, and is it open source and free and stuff? Yes, it's open source and free, although as you'll see I have made a GitHub repo for this, but there's nothing there at the moment because I'm planning to set up the GitHub repo while this video is rendering. It's probably going to take hours and hours, so I'm sure that by the time this video goes up, there will actually be some code here to get. So that's where you can get it from. I would caution you not to get too excited about making contributions or anything yet, because it's in a bit of a mess. And for example, my main.cpp file is like thousands of lines long. It needs to be tidied up and organized a lot better before I would expect anybody to even look at it. But if you want to try building it and running it just to see what the client feels like to run, that should work on Linux at least. On macOS, I'm not too bothered if it doesn't work very well there, but if it doesn't work on Fedora or Ubuntu, let me know about that and I'll definitely fix that. But yeah, don't get too excited about digging into the details just yet, because there's probably going to be a huge upheaval at some point in the not too distant future, and everything's going to be changed around quite a lot. And one last thing before I finally finish this video. God, this has taken a long time to make. I can't believe. I knew it was going to take a long time, but even so, oh my God, I'm actually in shock at how long this has taken. Yeah, so the last thing is, I think it's about time that iForce2D tried a little bit of e-begging, because I got to tell you, my finances are not in such a great state these days. And sometimes people tell me I should try Patreon and all that stuff, but it's never really appealed to me because it just feels a little bit, dirty somehow. I know that's a bit silly, but anyway. But I discovered that GitHub does sponsorships. So if you look down here, there's a sponsor button on this project and also on the other ones that I showed you as well. And I like this because they don't take a cut. Patreon takes 5%, I think, which is pretty crazy because all they do is sit there and take some money and pass it on. It doesn't really seem like it's worth 5%. But anyway, somehow GitHub is not taking a cut. And I feel like this is a little bit more focused or targeted on some specific project as well. Whereas for Patreon, you give somebody money and who the hell knows what it's for really. Well, I mean, there's assumptions, I suppose, about what's going to happen. But, you know, I feel that like this GitHub thing is a little bit more focused and targeted. And so anyway, that's what I'm going to try. I did make a Patreon account the other day. If anybody feels like discovering that, it's out there, but I'm not going to push that, at least for a while maybe. So if anybody's feeling generous and they want to see this project carry on and succeed, and they want to give me motivation to work on it more than I otherwise would if I was just working on it for myself, that would help out a great deal. In fact, I think the first thing it would be nice to get my hands on is a Raspberry Pi 5, so I could figure out the SPI interface with the weenyPRU for that. That would be interesting. But like I say, yeah, my finance is not too great these days. Since the beginning of COVID, get this, expenses like, you know, rent, electricity and food have gone up approximately 20%, but my salary has gone down by about 30%, and that's because I'm getting paid in Japanese yen, and the exchange rate is terrible. It's the Japanese yen versus New Zealand dollar is the lowest it's been in, I think, 37 years at the moment. So that's not particularly fun. That's why I've finally been driven to do this. So I think we're finally done with this video. It's like 2.5 hours. All right, so if anybody's still there, thanks for watching, and I'll see you next time.